Right now, as you settle in and get ready to sleep, something strange is happening inside your phone. GPS, satellites above your head, 24 of them in orbit, and your phone can see at least 4 at any given moment, are solving differential equations to pinpoint exactly where on the surface of the Earth you are lying. Each satellite carries atomic clocks accurate to the nanosecond and broadcasts a radio signal stamped with the time. Your phone calculates the difference between when the signal was sent and when it arrived, multiplies by the speed of light, and gets the distance to the satellite. 4 distances, 4 satellites, and a system of equations corrected by formulas from general relativity gives your coordinates to within a few feet. The audio compression algorithm in your earbuds is decomposing the soundtrack into an infinite sum of sine waves, a method invented 200 years ago by a French mathematician who was studying how heat spreads through a metal rod.
And somewhere in a data center, a neural network is learning to generate text, and in every training cycle, it applies the chain rule of differentiation, a formula that Gottfried Leibniz wrote down in 1676, sitting in his study in Hanover, with no idea that 3.5 centuries later, this formula would be running inside machines capable of holding a conversation in human language. All of this is calculus, one and the same mathematics, one and the same set of ideas, one and the same way of thinking about the world. 3 fundamental concepts: limit, derivative, integral. And from them flows all of modern science, all of engineering, all of physics, and a substantial part of economics, biology, and computer science. When you hear the word calculus, you might picture a fat textbook crammed with formulas, or recall a miserable exam, or feel that it is something incomprehensibly difficult, meant for a special kind of brain.
But behind those formulas lies one of the most beautiful and, at its core, one of the simplest ideas in the history of human thought. An idea that people in vastly different corners of the world, across vastly different eras, arrived at again and again. Because it is natural. Because it is the answer to a question you cannot help but ask if you observe the world around you. How do you describe something that never stops changing? And that answer has a history. Long, tangled, sometimes tragic, stretching across 4,000 years and spanning civilizations that never heard of one another. And here is what is truly astonishing. These civilizations, separated by thousands of miles and centuries, kept arriving at the same ideas. The Egyptians, 2,000 years before the Common Era, somehow produced a formula whose rigorous proof requires integral calculus.
The Babylonians in the same epoch calculated the distance Jupiter travels across the sky by adding up the areas of trapezoids under a velocity graph, and were essentially performing integration, although the word itself would not exist for another 3 millennia. Archimedes, on Sicily, around 250 years before the Common Era, inscribed an infinite number of triangles inside a parabola, approaching the exact answer through infinite approximation, and was doing precisely what we now call taking a limit. And in the 14th century in Kerala, on the southwestern coast of India, a mathematician named Madhava of Sangamagrama and his students developed infinite series for sine, cosine, and arctangent, 250 years before the same thing was done in Europe. As if the ideas were hanging in the air, waiting for someone to reach out.
And then, in the 17th century, 2 men, Isaac Newton in England and Gottfried Leibniz in Germany, gathered all of these scattered threads into a single system. Both of them, independently, within the span of a single decade, created calculus, a universal tool for understanding change. And they ignited one of the ugliest intellectual wars in the history of science. A war that split European mathematics into two camps, set British science back by an entire century, and ended with one of the two geniuses buried like a vagrant, almost without ceremony, forgotten by the patrons who had supported him for decades. Tonight we will tell this story in full, from the clay tablets of Mesopotamia to gradient descent in neural networks, from the first tentative brush with infinity to the mathematics that literally defines the shape of modern civilization. Along the way, we will figure out what calculus actually is, not as a set of formulas for an exam, but as a way of thinking.
We will understand what a limit means, why the derivative answers the question, how fast? Why the integral answers the question, how much in total? And why the discovery that these two questions are opposite sides of the same coin may be the most stunning intellectual breakthrough of the last 4 centuries. A few questions to guide our journey. How did ancient civilizations stumble onto the deepest ideas of mathematics thousands of years before anyone had the language to describe them? Why did humanity keep finding the same ideas and keep losing them? What exactly did Newton and Leibniz do that their predecessors did not, given that the individual pieces had existed long before them? Why did the fiercest war in the history of mathematics erupt between two people who, in all likelihood, arrived at the same result entirely on their own?
How is it possible that all of calculus stood on a logically shaky foundation for a century and a half, yet delivered flawlessly accurate answers? And why does the same mathematical gesture that Archimedes used 2,300 years ago, approaching an answer through an infinite number of steps, work today inside every neural network on the planet? And one more question, perhaps the most unexpected of all. Is calculus really as hard as people say? Or is its reputation as an impossible subject an artifact of how it is taught rather than what it is made of? Because here is the funny thing. The entire idea of calculus boils down to 2 questions. How fast is this changing? The derivative. How much has accumulated? The integral. 2 questions that every person who watches the world asks themselves. A driver glancing at the speedometer is looking at a derivative. An accountant closing the books for the quarter is computing an integral.
A doctor measuring how fast a tumor is growing is estimating a derivative. A meteorologist tallying how much rain fell in a month is taking an integral. The answers to all of these questions are connected, and they will reveal themselves gradually as we go deeper. And here is one more question, perhaps the most personal of all. Why does calculus have a reputation for being impossibly difficult, when at its core are ideas that any person capable of watching something move and asking, how fast and how much, can understand? By the end of our journey, you will know the answer, and you may discover that calculus itself is not a hostile labyrinth, but something surprisingly natural, almost obvious, once you see it not as a pile of formulas to memorize, but as the story of people who tried to precisely describe a world where everything is continuously changing. Think of it as layers. Each era is a new layer, and in each layer a different civilization, a different mind, a different system of writing, but one and the same dream: to understand a world that never stands still. We will start at the very bottom, with the times we know only from clay tablets and scraps of papyrus. From there we will rise to Archimedes, the man who first systematically approached infinity and used it to get exact answers. Then we will see how the same ideas, as if obeying some law of nature, kept surfacing in the minds of people on other continents, in China, in the Islamic world, in India. Then, 17th century Europe, the moment when the scattered pieces finally came together and 2 men, Newton and Leibniz, simultaneously and without knowing of each other, created the tool that would change everything. We will take apart what that tool does, how it works, and why it works. We will see the crisis that erupted when it turned out that the foundation everything rested on was logically unsound, and the people who rebuilt that foundation. And finally, we will surface into the present day, into the world of neural networks, GPS, medical imaging, and data compression, and see that the very same mathematics whose seed Archimedes held in his hands is running inside every one of these technologies. Get comfortable. The journey is long, but there is no need to rush. Every era will get as much time as it needs. Every idea will be explained slowly, with examples, with analogies, with concrete numbers. If something feels difficult, do not worry. We will come back to it from another angle, explain it differently, give another example. Calculus deserves to be understood, and it can be understood. We begin at the very bottom, with clay tablets and papyrus scrolls. Around 1820 before the Common Era, roughly 4,000 years ago, someone in Egypt wrote down a series of mathematical problems on a sheet of papyrus. We do not know who. We do not know who it was meant for. A student, a temple scribe, an engineer building a granary. All we know is that the scroll survived to our day, and that it contains a formula that makes modern mathematicians literally catch their breath. The scroll is called the Moscow Mathematical Papyrus, after the city whose museum holds it now. It was acquired by the Russian Egyptologist Vladimir Golenishev in the late 19th century, and later transferred to the Pushkin Museum of Fine Arts in Moscow. The papyrus contains 25 problems, most of them practical in nature, computing areas, volumes, distributing grain and bread. But among them is one that stands apart. Problem number 14.
It asks you to calculate the volume of a frustum, the shape you get when you take a pyramid and slice off the top with a horizontal cut. Picture the Great Pyramid of Giza with its tip sheared off, a square base at the bottom, a smaller square base on top, and sloping walls in between. Frustums are everywhere in Egyptian architecture: the bases of obelisks, the pedestals of statues, the steps of pyramids. The problem was practical. How much stone do you need for a block like this? The problem gives concrete numbers: a lower base with a side of 4, an upper base with a side of 2, a height of 6. And it offers a method of calculation that, written in modern language, looks like this. The volume equals 1/3 of the height times the sum of the area of the lower base, the area of the upper base, and the product of the sides of both bases.
In a formula,
V equals h over 3 times the quantity a squared plus a times b plus b squared, where a and b are the sides of the square bases, and h is the height. And here is what is staggering. The formula is perfectly exact. Not an approximation, not a rough estimate, not good enough for construction. It is mathematically flawless. When modern mathematicians first read this problem, they were genuinely stunned, because rigorously deriving this formula requires integral calculus. You need to be able to sum up infinitely many infinitely thin horizontal slices of the pyramid, whose area changes as you rise from the base to the top. That is, in essence, a definite integral, a concept that would not be formalized for another 3,500 years. How did the Egyptians arrive at it? Honestly, we do not know. They had no algebra in our sense. They had no variables, no symbols for generalized quantities. They worked with specific numbers, specific problems, specific shapes. Perhaps they arrived at the formula empirically, through measurements and observations. Perhaps they built physical models and spotted the pattern. Perhaps there was a chain of reasoning that never reached us. All we see is the result, and the result is flawless. Try to picture the scene. Some temple in Upper Egypt, the heat, a reed pen on papyrus. A scribe is working on a problem that is, in all likelihood, tied to a practical need, perhaps estimating a granary, or calculating how much stone to order, or something else we can only guess at. He has no abstract variables. He writes specific numbers. He has no general algebraic formula. He records a sequence of arithmetic steps. Square the side of the lower base. Square the side of the upper base. Multiply the sides of both bases together. Add the three results. Multiply by 1/3 of the height.
And this sequence of steps, this concrete recipe for concrete numbers, turns out to be a perfect embodiment of a general formula that works for any frustum with a square cross-section. We are used to thinking of mathematics as progress, from simple to complex, from imprecise to precise. But the Moscow papyrus disrupts that picture. The result recorded in it is not an approximation, it is perfectly exact. And its rigorous justification, the proof that the formula is always correct, not just for these particular numbers, requires methods that we associate with a far later era. Think about what this means. 4,000 years ago, in a civilization that had none of the tools we consider essential for serious mathematics, someone arrived at an answer that requires integration. They did not realize they were doing anything beyond arithmetic and geometry. They were solving a practical problem, probably related to construction. But the mind that found that answer touched something very deep. There are other traces of proto-calculus in Egyptian mathematics. The Rhind papyrus, another mathematical papyrus from roughly the same period, contains problems on computing the areas of circles. The Egyptians used an approximation. The area of a circle is roughly the area of a square whose side is 8/9 of the diameter. If you work it out, this is equivalent to a value of pi of about 3.16, which, for practical purposes, building granaries, digging canals, was perfectly adequate. But notice, to compute the area of a circle, you need to somehow get from a curved shape to a straight-lined one. The Egyptians did it crudely, replacing the circle with a square. Archimedes, 1,500 years later, would do it exactly, through infinite approximation. The evolution of the method, from rough approximation to infinitely precise, is the road to calculus. Now let us move east, to Mesopotamia, to the same epoch, roughly 1,800 years before the Common Era. The valley between the Tigris and the Euphrates, the territory of modern-day Iraq, one of the cradles of human civilization. Writing, laws, astronomy, mathematics, all of these were born here, among the earliest in the world. The Babylonians kept records on clay tablets, and some of these tablets have survived to our day in remarkably good condition. Clay, unlike papyrus, does not rot or burn. In fact, fire only strengthens clay by baking it. When the library of Ashurbanipal in Nineveh was torched, the tablets did not perish, but hardened. Among the hundreds of thousands of tablets stored in museums around the world, there is a group of astronomical records, and here is what is remarkable. The Babylonians were obsessed with predicting celestial events, eclipses, planetary positions, phases of the moon. All of this carried not only practical but religious significance.
Astronomer priests were among the most influential people in the society. And here is what they did with Jupiter. Jupiter, the largest planet in the solar system, was one of the brightest stars in the Mesopotamian night sky. A bright dot that, unlike real stars, slowly drifted against the background of fixed constellations. The word planet comes from the Greek planetes, meaning wanderer. Planets wander among the stars, while stars keep their relative positions. Jupiter moves across the night sky, and its apparent speed changes. Sometimes it moves faster, sometimes slower. Sometimes it appears to stop and reverse direction. This is called retrograde motion. caused by the difference in the orbital speeds of Earth and Jupiter around the Sun. When Earth overtakes Jupiter on its inner orbit, an optical illusion makes Jupiter appear to move backward, much like a car you are passing on the highway seems to drift backward from your window.
Babylonian astronomers wanted to predict exactly where in the sky Jupiter would be after a certain period. 60 days, 120 days. This mattered for religious ceremonies, astrological predictions, and the calendar. To do this, they needed to calculate the total distance, or rather, angular displacement, Jupiter would travel across the sky, knowing how its speed changed from day to day. And here is what they did. They drew something like a graph, with time along one axis and Jupiter's speed along the other. Then they calculated the area of the figure underneath this graph by breaking it into trapezoids. They added up the areas of the trapezoids and got the total distance traveled. It is worth clarifying that the Babylonians did not draw graphs in our sense. They had no coordinate plane. They worked with tables of numbers recorded in cuneiform on clay. But the logic of their calculations matches exactly what we do today when we compute the area under a curve. Break it into simple shapes, trapezoids, compute the area of each, add them up. The historian of mathematics Mathieu Ossendriver, who studied Babylonian astronomical tablets at the British Museum, published a paper in 2016 showing that Babylonian astronomers used geometric methods to track Jupiter, methods that anticipated European mathematics by 14 centuries. Picture it. The night sky over Mesopotamia, a priest astronomer, a clay tablet, and a reed stylus. He is recording observations of Jupiter, a bright point slowly crawling among the fixed stars. He wants to know where Jupiter will be in 60 days, and his way of finding out is, in essence, numerical integration. Let us pause and think about why this matters so much. The point is not that the Babylonians were smarter than we thought. That is a condescending framing that misses the deeper significance. The point is that certain mathematical ideas do not seem to be inventions in the usual sense of the word. They are closer to discoveries, to something that exists in the structure of reality itself, waiting for someone to notice. The Babylonians did not invent integration. They ran into a problem where change was not constant, and the only way they could cope, breaking a continuous process into small chunks and adding them up, led them to the same technique that Riemann would formalize 3.5 millennia later when he defined the definite integral. But, and this is the crucial point, neither the Egyptians nor the Babylonians took the next step. They solved specific problems using incredibly clever tricks. They found the area of this particular frustum. They computed the distance for this particular trajectory of Jupiter. They did not stop and say, "Wait, there is something universal here. There is a method that works for any shape, any graph, any process of change." That abstraction, the ability to take a trick that works in one situation and turn it into a general method applicable to any problem, would come later. And it would come gradually, piece by piece, from the most different corners of the world. But before we move on, it is worth pausing to appreciate what these early civilizations accomplished. They did not know they were doing calculus. They had no words for what they were doing. They saw a concrete problem, the volume of a stone block, the trajectory of a planet, and found a way to solve it. And the way they found turned out to be the same one that, millennia later, would be formalized, named, put into textbooks, and taught to millions of students. This is the first lesson of our story. Calculus is not the invention of one person, one moment, or one era.
It is the answer to questions that inevitably arise whenever an intelligent being tries to precisely describe change. And because change is a fundamental property of reality, that answer will be found again and again in any sufficiently developed civilization, regardless of language,
script, or cultural tradition. The second lesson. At this early stage, every solution had a ceiling. Every method was tied to a specific problem. The frustum formula worked for frustums. The trapezoids worked for Jupiter. Generalization did not happen, not because the people were not brilliant, but because generalization requires a different level of abstraction. You need variables, you need a coordinate system, you need a way of talking about arbitrary curves and arbitrary functions. All of that would come, but thousands of years later, and in another part of the world.
The first person who pushed this idea further than anyone else in the ancient world lived on the island of Sicily, in the city of Syracuse, roughly 1500 years after the Moscow Papyrus. His name was Archimedes, and what he did with a parabola was so profound that 2,000 years later, mathematicians would still cite his method as the first true step toward what we today call calculus. But Archimedes belongs in the next chapter. For now, hold on to this picture. 4,000 years ago, in the heat of the Mesopotamian plain, someone was drawing trapezoids under a curve of Jupiter's speed and adding up their areas. That person had no idea they were doing something that, thousands of years later, would become the foundation of engineering, physics, economics, and artificial intelligence. They just wanted to know where Jupiter would be next month. Sometimes, the deepest ideas are born from the most practical questions. Picture Syracuse, roughly 250 years before the Common Era. A city on the eastern coast of Sicily, the largest island in the Mediterranean. One of the biggest and wealthiest cities in the Greek world, larger and richer than Athens itself by that point. A population of perhaps 500,000, the harbour packed with merchant ships from Carthage, Egypt, Greece, Rome. The city walls thick and tall. Syracuse knows that sooner or later, the Romans will come. The Roman Republic is expanding, and Sicily is a strategic prize, controlling the sea lanes of the Mediterranean. And somewhere in this city, perhaps in a workshop, perhaps in a library, perhaps in a bathhouse — the Greeks loved to discuss mathematics in bathhouses — lives a man who, by the general consensus of historians of mathematics, was the greatest mathematician of antiquity. Perhaps one of the greatest in all of human history, standing alongside Newton, Gauss, and Euler. Archimedes was born around 287 before the Common Era. We do not know much about his life. Most biographical details come to us through later retellings, especially through Plutarch, writing 3 centuries after the fact. The famous Eureka story about King Hieron's crown may be apocryphal, although the underlying principle, determining density through water displacement, is perfectly valid and still in use today. Archimedes' father was reportedly an astronomer and possibly a relative of King Hieron II, ruler of Syracuse. Archimedes most likely studied in Alexandria, the greatest scientific center of the ancient world, the city of the Great Library and the Museion, where he may have mingled with students of Euclid. Upon returning to Syracuse, Archimedes devoted his life to mathematics and engineering. He invented the Archimedean screw for lifting water, a device still in use today. He designed war machines, catapults and cranes that defended Syracuse against the Roman fleet during a siege. Plutarch wrote that Roman soldiers retreated in terror whenever they saw a beam or a rope appear above the city walls, thinking Archimedes had aimed yet another weapon at them. But the mathematics he pursued in quiet was more significant than any war machine. And the deepest thing he did was tied to a problem that sounds deceptively simple. Find the area of a shape bounded by a parabola. A parabola is that smooth, U-shaped curve you may remember from school, the graph of y equals x squared. The curve a ball traces when thrown at an angle. The shape the surface of water takes in a spinning bucket. A parabola has curved edges, and areas are easiest to compute for shapes with straight edges. Rectangles, triangles, polygons. How do you find the area of something whose boundaries curve? Archimedes had no algebra, no variables, no formulas in our sense, no coordinate system. Descartes would invent that 2 millennia later. Archimedes had geometry, a set of shapes whose areas he knew how to compute, and his own mind. Nothing else. And here is what he came up with. He took the parabola and inscribed one large triangle inside it, the biggest one that fits inside the parabolic region. The triangle covers a significant fraction of the area, but between its sides and the curve of the parabola there remain gaps, small crescent-shaped slivers that the triangle missed. Then, Archimedes filled each of those gaps with another, smaller triangle. Now the shape was better covered, but new gaps appeared, even tinier. He filled those too, with even smaller triangles. And he kept going. Each step added more and more triangles, tinier and tinier, filling ever narrower cracks between the polygonal approximation and the actual curve. With each step, the total area of all the triangles crept closer and closer to the true area of the parabolic region. The gaps narrowed, the error shrank. And if you continue this process forever, adding infinitely many infinitely small triangles, the sum converges to the exact answer. Archimedes had no word for limit. He had no notation, no algebraic machinery, not even the modern concept of infinity. But what he was doing was the deepest move in all of calculus. He was chasing an exact value, getting closer and closer, never touching it directly, but knowing that the difference between his approximation and the true answer could be made as small as he liked. This idea that you can pin down something exactly by approaching it through an infinite number of steps, Archimedes applied again and again. He found the area of a circle by inscribing regular polygons with more and more sides. A hexagon, a 12-sided polygon, a 24-sided polygon, and so on. With each doubling of the number of sides, the polygon hugged the circle more tightly, and its area crept closer to the area of the circle. In the limit, a polygon with infinitely many infinitely short sides, you get the circle itself. Using this method, Archimedes computed the ratio of the circumference to the diameter, the number we now call pi, and showed that it lies between 3 plus 10 over 71 and 3 plus 1 over 7. For the 3rd century before the Common Era, this is astonishing accuracy. He found the volume of a sphere, 2/3 the volume of the circumscribing cylinder, a result he was so proud of that he asked for a sphere inscribed in a cylinder to be engraved on his tombstone. The Roman orator Cicero, visiting Syracuse about a century and a half after Archimedes' death, tracked down his grave among the overgrowth and actually saw the engraving on the crumbling stone. He found the surface area of a sphere, 4 pi r squared, exactly equal to the area of 4 great circles. He computed the area of an ellipse, pi times a times b, where a and b are the semi-axes. He found the area of the spiral, later named after him. He computed the slope of the tangent to that spiral, which is, incidentally, an early precursor to the derivative, the second of the two fundamental operations of calculus. And all of this through purely geometric reasoning, without a single algebraic formula, case by case, figure by figure. Let us trace through this process one more time, slowly, because the seed of all of calculus is in it. Step 1. The big triangle. Covers, say, 2/3 of the area. Error, 1/3. Step 2. Two smaller triangles in the gaps. Total covered area grows. Error shrinks. Step 3. 4 even smaller triangles. Area even closer to the true value. Error even smaller. And Archimedes showed, rigorously, geometrically, that at each step the error shrinks by exactly a factor of 4. After the first step, the error is 1/3 of the area. After the second, 1/12. After the third, 1/48. After n steps, the error equals 1/3 times 1/4 to the nth power. As n grows, this quantity approaches 0. The sum of all the triangles approaches the exact area of the parabolic region. And the result he obtained is stunningly elegant. The area of the parabolic segment equals 4/3 the area of the inscribed triangle. Not approximately 4/3, exactly 4/3. A precise, simple, beautiful ratio obtained through an infinite process. This method, infinite approximation through ever more accurate approximations, later came to be called the method of exhaustion. The term is somewhat misleading because it suggests you are exhausting the area by filling it with pieces. The actual idea is subtler. You are exhausting the possibility of error. With each step, there is less and less room for your approximation to differ from the truth. And here we should stop and talk about what makes Archimedes' method so important for our story, because this is the key to everything that follows. This is the core from which all the mathematics we will discuss for the rest of our journey will grow. The essence is this. All of calculus, all 3.5 centuries of its formal history, all of its theorems, all of its applications, is built around one idea. 1. Everything else, derivatives, integrals, series, differential equations, is a consequence, an application, an extension of this one idea. If you understand it, everything else is technique. The idea is this. You can get an exact answer by considering an infinite process of approximation. Not a good answer, not accurate enough. Exact. Perfectly exact. Through an infinite process. This seems paradoxical. How can an infinite process yield a finite, definite result? But it can, and Archimedes was the first to demonstrate this systematically. You cannot measure the circumference of a circle with a ruler. It curves, and a ruler is straight. But you can inscribe a hexagon inside the circle and measure its perimeter. Not very accurate. A hexagon is a rough approximation of a circle. A 12-sided polygon is better. A 24-sided polygon, better still. A polygon with 1,000,000 sides, its perimeter will be so close to the circumference that no instrument could tell the difference. And if you mentally pass to a polygon with infinitely many sides, polygon and circle become one and the same. You get the exact answer. You cannot find the speed of a car at a specific instant, because in a single instant there is no motion. But you can measure the average speed over a second. Over a 1/10 of a second, more accurate. Over a 1,000th, even more. Over a 1,000,000th. So accurate that for any practical purpose, it is the instantaneous speed. In the limit, as the interval shrinks to 0, you get the instantaneous speed, the one the speedometer shows. You cannot finish an infinite subdivision, but you can describe where the process leads and prove that it leads to one and only one value. The limit is not the last step of an infinite process. There is no last step. The limit is the value the process inevitably closes in on, the value it surrounds from all sides, leaving less and less room for any alternative. You cannot add infinitely many numbers if each one is finite and non-zero. The sum would blow up to infinity. But if the numbers shrink fast enough, the sum can converge to a finite number. 1 plus 1/2 plus 1/4 plus 1/8. Go on as long as you like. In the limit, the sum is exactly 2. All of these situations are the same idea. Approach without touching. Get an exact answer from infinitely many approximate steps. Archimedes was the first to show that this method works, that it can be trusted, that results obtained this way are no less rigorous than the results of ordinary geometry. Let us see how he proved it for the circle, because this example is even more vivid than the parabola. Archimedes inscribed a regular hexagon inside the circle. The hexagon's perimeter is a lower bound for the circumference, its area a lower bound for the area of the circle. Then he circumscribed a regular hexagon around the circle. Its perimeter and area give upper bounds. The circle is sandwiched between the two hexagons, like a filling in a sandwich. Then he doubled the number of sides, 12-sided polygons, inscribed and circumscribed. The gap between the upper and lower bounds narrowed. 24 sides, narrower still. 48, even narrower. 96. And Archimedes stopped, because the calculations were becoming overwhelming. Remember, no decimal fractions, no calculator, not even a positional number system, just fractions. With 96 sides he obtained 3 plus 10 over 71 is less than pi, which is less than 3 plus 1 over 7. That is, 3.14084 is less than pi, which is less than 3.14285. For the 3rd century before the Common Era, astonishing accuracy. He proved it by contradiction. Suppose the area of the parabolic region differs from my answer. Then the difference between them is positive. Call it epsilon, a letter that, 2 millennia later, would become the standard symbol for an arbitrarily small positive quantity. But I can add enough triangles to make the error smaller than epsilon. And since the error can be made smaller than any given epsilon, there is no error. My answer and the true area are the same.
This logic, for any given error I can make the approximation accurate enough, would become, 2,000 years later, the formal definition of the limit. Cauchy and Weierstrass would essentially rewrite Archimedes' logic in algebraic language. But the scaffolding, the idea that accuracy is defined through the impossibility of error rather than through an infinite number of steps, belongs to Archimedes. But he did not plant the seed, and here is why. Archimedes worked within the Greek mathematical tradition, which viewed infinity with deep, philosophically grounded suspicion. The Greeks had a developed philosophy of mathematics. Questions about the nature of numbers, the existence of mathematical objects, and the permissible methods of reasoning were discussed seriously and systematically. Aristotle, who lived a generation before Archimedes, drew a sharp line between two types of infinity. Potential infinity was acceptable. You could say, the process can be continued as far as you like. You can always add 1 to any number. A segment can be divided endlessly. But actual infinity, infinity as a completed object, as something existing all at once, was forbidden. You could not say, an infinite set of points. You could say, as many points as you wish. The difference sounds verbal, but it is philosophically deep and mathematically significant. This prohibition was not a whim. Behind it stood the paradoxes of Zeno, which showed that infinity, handled carelessly, breeds logical monsters. Zeno of Elea, who lived in the 5th century before the Common Era, formulated several arguments that mathematicians could not rigorously refute for more than 2,000 years. The most famous is Achilles and the tortoise. Achilles runs 10 times faster than the tortoise.
The tortoise gets a head start of about 330 feet. By the time Achilles covers that distance, the tortoise has crawled about 33 feet. By the time he covers those 33 feet, it has crawled about 3 feet 4 inches. By the time he covers that, it has moved about 4 inches, and so on, infinitely. Every time Achilles reaches the spot where the tortoise was, it has moved a little farther. Therefore, Zeno concludes, Achilles never catches the tortoise. Another of Zeno's paradoxes, the dichotomy, poses the same problem even more sharply. To get from point A to point B, you first have to cover half the distance, then half of the remaining half, then half of that, and so on, infinitely. Before you reach B, you must complete an infinite number of steps. But an infinite number of steps cannot be completed. Therefore, motion is impossible. And then there is the paradox of the arrow.
A flying arrow at each specific instant occupies a definite position in space. At each instant it is motionless. It is at that location. But if it is motionless at every instant, when does it move? Is motion a sum of rests? How can a sum of zeros yield something non-zero? Of course, in reality, Achilles catches the tortoise without trouble. Arrows fly, and we walk from point A to point B every day. But Zeno was asking a question not about reality, but about logic. If space and time are infinitely divisible, and if getting from A to B requires passing through infinitely many intermediate points, how do you finish an infinite process? How do you take infinitely many steps in finite time? The answer, through the concept of limits and convergent series, was rigorously formulated only in the 19th century. Until then, Zeno's paradoxes remained a thorn in the side of mathematics, and it was precisely because of them that the Greeks were so cautious with infinity. Archimedes, for all his genius, worked within these constraints. Every one of his proofs was conducted by contradiction. He avoided directly asserting, after infinitely many steps, the process is complete. Instead, he would say, suppose the result differs from mine, then I will show a contradiction. This allowed him to get correct answers without crossing the forbidden line drawn by Aristotle. But the cost of this caution was steep. Each problem demanded a separate, specially constructed geometric argument. For the parabola, one set of triangles and one geometric progression. For the circle, another set of polygons and other calculations. For the spiral, a third trick. Archimedes had no general algorithm, no recipe that could be applied to any curve, any area, any problem involving change. Compare this to what Newton would do. The power rule, one formula for the derivative of any power function. The chain rule, one formula for the derivative of any composition.
The fundamental theorem, one statement linking integration and differentiation for any continuous function. Newton and Leibniz would build a machine, a mechanism that works for all problems. Archimedes created works of art, each unique, each requiring mastery and ingenuity, but none transferable to the next problem. His method was art, not technology. The difference between art and technology: art demands talent for every piece. Technology encodes talent into a procedure that any trained person can repeat. Calculus would become technology, and that is precisely why it would change the world. And yet, Archimedes saw more than he revealed in his published works. In the 20th century, an astonishing document was discovered, the so-called Archimedes palimpsest. This is a parchment on which a medieval monk scraped off the original text and wrote prayers over it. Using modern technologies, X-ray fluorescence and other methods, scientists managed to read the original beneath the prayers. And it turned out to be a copy of a previously unknown treatise by Archimedes, in which he described his real method, the one he used to find answers before clothing them in rigorous geometric proofs. In that treatise, Archimedes mentally sliced figures into infinitely thin strips and weighed them on imaginary scales using a lever. He worked with infinity directly, exactly the way Aristotle said you must not. He knew his method was not a rigorous proof by the standards of Greek mathematics, but he used it as a tool for finding answers, which he would then prove formally. The story of the palimpsest's discovery deserves a mention in its own right. In 1906, the Danish philologist Johann Ludwig Heiberg found the parchment in a monastic library in Constantinople. He read part of the text and realized that Archimedes lay hidden beneath the prayers. Over the 20th century, the parchment was lost, resurfaced in a private collection, and in 1998 was sold at auction to an anonymous buyer for $2 million. The buyer sent it for study to the Walters Art Museum in Baltimore, where a team of scientists using synchrotron X-ray radiation managed to read most of the original text. And what they read forced historians to reconsider Archimedes' place in the history of mathematics. In the treatise, titled The Method, Archimedes described not the final proofs, but the process of thinking, how he found answers before translating them into the language of formal geometry. And that process involved direct work with infinitesimals, with infinitely thin strips, with weighing geometric figures on a lever, with reasoning that anticipated Cavalieri's approach by 19 centuries. This means Archimedes was even closer to calculus than we thought. He was not merely approaching exact answers. He was thinking in terms of infinitesimal quantities. The very infinitely thin strips that, 2 millennia later, would become the basis of Leibniz's approach. But he kept these ideas secret because he knew they would not withstand logical scrutiny by the standards of his time. Archimedes died in 212 before the Common Era, when the Romans finally took Syracuse after a 2-year siege. According to legend, the Roman general Marcellus ordered that Archimedes not be harmed. He respected the man's genius and wanted to capture him alive. But in the chaos of the assault, a soldier who did not know or did not remember the order found an old man bent over a geometric diagram drawn in the sand. "Do not disturb my circles," Archimedes reportedly said. The soldier killed him. Marcellus, upon learning what had happened, was, according to Plutarch, furious and grief-stricken. He ordered that Archimedes' relatives be found and cared for. He arranged a proper burial. On the tombstone, at Archimedes' own wish, was carved a sphere inscribed in a cylinder. Whether all of this is true, we do not know. But we do know that with his death, the thread he had been pulling, the thread of infinite approximation, the thread of proto-calculus, was severed. No one in the ancient world picked up his methods at the level where he had left them. Severed for a long time. At least in the Mediterranean world. After the fall of the Western Roman Empire in the 5th century of the Common Era, Europe sank into a period that historians once called the Dark Ages, though the term is imprecise and outdated. Mathematics in Europe did not vanish but froze. Monasteries preserved manuscripts but did not develop their content. Practical arithmetic for trade and surveying continued, but theoretical mathematics capable of advancing Archimedes' ideas was all but absent. But not in the rest of the world, because the same ideas, as if obeying some law of nature, some mathematical equivalent of convergent evolution in biology, kept surfacing in the minds of people on different ends of the earth. And some of those people went considerably further than Archimedes had. We leave Syracuse and head east, first to China, then to Baghdad, and then to the southwestern coast of India. In each of these places, a person awaits us who, knowing nothing of Archimedes, arrived at the same ideas, and sometimes went well beyond them. In the 3rd century of the Common Era, roughly 500 years after Archimedes, a mathematician named Liu Hui lived in China. We know even less about his biography than about Archimedes. He worked in the Kingdom of Wei and wrote commentaries on an ancient Chinese mathematical treatise called The 9 Chapters on the Mathematical Art, a collection of problems that served as something like a standard textbook for officials and engineers. And here is what is remarkable. Liu Hui, knowing nothing of Greek mathematics, independently invented the method of exhaustion. He wanted to compute the area of a circle, and he approached it the same way Archimedes had. He inscribed a regular polygon inside the circle and kept increasing the number of sides. A hexagon, a 12-sided polygon, a 24-sided polygon. With each doubling, the polygon pressed tighter against the circumference, and its area crept closer to the area of the circle. Liu Hui pushed the number of sides to 3,000 and beyond, computing pi to 5 decimal places. The same idea. A different continent, a different era, a different language, a different notation, a different mathematical tradition, but the same deep move. Approximate the curved with the straight. Make the approximation as accurate as you please. Get the answer in the limit. Liu Hui went further still. He did not merely use the method of exhaustion as a computational trick, he reflected on it. He understood that with each doubling of sides the error shrank, and he discussed how far you could carry the process. In his reasoning we can see the seeds of the idea of convergence. He did not formalize it. Formalization was still 1,500 years away, but the intuition was there. After Liu Hui, the work in China was continued by Zhu Chongji in the 5th century, who pushed the computation of pi to 7 decimal places, 3.1415926, a record that held for nearly 1,000 years. Zhu Chongji's exact method is unknown, his manuscripts are lost, but he apparently used polygons with an enormous number of sides, and the sheer volume of hand calculation was staggering. The patience and persistence are remarkable. The method was the same as Archimedes. This coincidence is one of the most eloquent pieces of evidence that the ideas of calculus were not the accidental invention of one person or one culture. They were the answer to a fundamental question that inevitably arises when you try to precisely describe a world where everything is curved and everything is changing. Straight lines and constant speeds are abstractions, convenient for reasoning, but nature is not confined to them. And the moment you run into a curved line or a changing speed, you face a choice. Either settle for approximations or find a way to go from approximation to exactness. The method of exhaustion is the second path. Now let us move to the Islamic world, to the golden age of Arabic mathematics, the period roughly from the 8th to the 14th century of the Common Era. This was an era when Baghdad, Cairo, and Cordoba were the intellectual capitals of the world. In Baghdad, the Caliph al-Ma'mun founded the House of Wisdom. Beit al-Hikmah, in the 9th century, an institution whose purpose was the systematic translation of scientific texts from Greek, Sanskrit, and Persian into Arabic. It was here that the works of Euclid, Archimedes, Apollonius, and Ptolemy were translated and preserved. Without these translations, a significant part of the Greek mathematical heritage would have been lost forever. Europe recovered Archimedes through Arabic translations, which in the 12th and 13th centuries were translated into Latin in Toledo and other centers of medieval Spain. But Arab scholars did not merely translate, they extended, expanded, and pushed mathematics further than the Greeks had. Among the many outstanding figures of this period, one who stands out is Ibn al-Haytham, Latinized as Alhazen, who lived from roughly 965 to about 1040. Ibn al-Haytham was born in Basra, in what is now Iraq, and spent a significant part of his life in Cairo at the court of the Fatimid Caliph al-Hakim. He is best known for his work on optics. His Book of Optics, Kitab al-Manazir, defined the understanding of light and vision in European and Islamic science for centuries. It was Ibn al-Haytham who showed that vision does not work the way the Greeks thought. Euclid and Ptolemy believed the eye emits visual rays, like a flashlight. But the other way around. Light reflects off objects and enters the eye. He investigated refraction, reflection, lenses, and the camera obscura. His method, systematic experimentation, testing theory against evidence, anticipated the scientific method by several centuries. But among his mathematical works, there is something directly connected to our story of calculus. Ibn al-Haytham worked on problems involving the summation of powers of natural numbers, sums of squares, cubes, fourth powers. This is exactly the type of problem that arises when you try to compute integrals of polynomial functions. If you want to find the area under the parabola y equals x squared from 0 to some value, one approach is to break the interval into n parts, estimate the area with rectangles, and compute a sum that includes 1 squared plus 2 squared plus 3 squared, and so on, up to n squared. The formula for this sum is the key step in computing the integral, and Ibn al-Haytham knew and used these formulas. Beyond that, Ibn al-Haytham developed early versions of what we now call the method of exhaustion for computing volumes of solids of revolution, shapes obtained by rotating a curve around an axis. He was essentially computing definite integrals, though he did not have that concept. It is also worth mentioning al-Khwarizmi, who lived in the 9th century and whose name gave us the word algorithm. Although his work was primarily algebraic rather than calculus-related, it was al-Khwarizmi who systematized algebra as a discipline and showed that mathematics could be not just a collection of problems and answers, but a system of methods, algorithms, applicable to entire classes of problems. This idea that a mathematical method can be universal, that the same recipe works for an infinite number of problems, is central to our entire story. Another figure, Omar Khayyam, better known in the West as a poet, the author of the Rubaiyat, but in reality a major mathematician. Khayyam worked with cubic equations using intersections of conic sections, and his geometric methods contained elements that would later find their way into Descartes' analytic geometry. The work of all these mathematicians, al-Khwarizmi, Khayyam, Ibn al-Haytham, and many others, influenced European science through a complex chain of translations and knowledge transfer. Through Moorish Spain, through Italy, where Fibonacci popularized the Arabic numeral system in the 13th century, through Latin translations of Arabic texts, these ideas made their way into Europe and became part of the intellectual environment in which calculus would grow. But the most astonishing chapter of our story before Newton and Leibniz unfolds neither in Europe, nor in the Middle East, nor in China. It unfolds on a small strip of coastline in southwestern India, in the region known today as Kerala. Here, around 1340, a man named Madhava of Sangamagrama was born. We know very little about his life. His own works have not survived, and we know of his results only through the writings of his students and followers, especially Nilakantha Somayaji, Jayastadeva, and others. The situation resembles that of Socrates. We know the teacher's thoughts through the students' records.
And what Madhava and his students, the group we now call the Kerala School of Astronomy and Mathematics, accomplished over the next 2 centuries, looks, from the perspective of a modern mathematician, almost unbelievable. The school endured from roughly 1350 to around 1550, 200 years of unbroken mathematical tradition, passed from teacher to student. They developed infinite series. Let us pause and explain what that means, because infinite series are one of the central constructions in all of calculus. And understanding what Madhava did is impossible without at least an intuitive sense of them. Imagine a sum with infinitely many terms. For example, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. Each term half the previous one. You might think that adding infinitely many numbers should give an infinite result. But it does not, because the terms shrink fast enough. Here is a simple way to see it. Imagine a segment 2 units long. Color half of it, that is 1 unit. Color half of what remains, 1/2. Half of what remains, 1/4. Half of what remains, 1/8. With each step, you cover another half of the uncolored space. You will never go past the 2-unit mark, because each new piece fits inside the remaining gap. In the limit, after infinitely many steps, the entire segment is colored. The sum equals exactly 2. You can also verify this algebraically. Let S equal 1 plus 1/2 plus 1/4 plus 1/8 and so on. Multiply both sides by 1/2. S over 2 equals 1/2 plus 1/4 plus 1/8 plus 1/16 and so on. Subtract the second from the first. S minus S over 2 equals 1. That is, S over 2 equals 1, so S equals 2. An infinite sum and a finite answer, obtained in 2 lines of algebra. This is a convergent series, an infinite sum that approaches a finite limit. There are series that do not converge. For instance, 1 plus 1 plus 1 plus 1, going on forever, obviously grows without bound. A subtler example: 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and so on, the so-called harmonic series. Each term gets smaller and smaller, and it seems like the sum should converge. But it turns out that it grows without bound, albeit slowly. It diverges. Why? Here is a simple proof, devised by the medieval mathematician Nicole Oresme in the 14th century. Group the terms. 1/3 plus 1/4 is greater than 1/4 plus 1/4, which equals 1/2. The next 4. 1/5 plus 1/6 plus 1/7 plus 1/8 is greater than 4 times 1/8, which equals 1/2. The next 8. 1/9 through 1/16 is greater than 8 times 1/16, which equals 1/2. Each such group contributes at least 1/2, and there are infinitely many groups. So the sum grows without limit. This is a counterintuitive result.
a series with shrinking terms whose sum is nevertheless infinite. The boundary between series that converge, like 1 plus 1/2 plus 1/4 plus, and series that diverge, like 1 plus 1/2 plus 1/3 plus, is one of the central topics of calculus. The line between convergence and divergence turns out to be thin and far from obvious. And that is precisely why Cauchy and Weierstrass would spend so much effort on rigorous definitions. So, Madhava and his school were working with infinite series long before the concept appeared in Europe. Specifically, they developed infinite series expansions for trigonometric functions: sine, cosine, and arctangent. The arctangent series that Madhava discovered is known in the European tradition as the Leibniz formula for pi, or the Gregory-Leibniz series. The name Leibniz series tells you whom Europe credited with its discovery.
But Madhava found it first, roughly 250 years before Leibniz and Gregory. Specifically, Madhava's series for pi over 4 looks like this. Pi over 4 equals 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, and so on. An infinite sum of reciprocals of odd numbers with alternating signs. Each successive term is smaller than the last, the signs alternate, and the sum oscillates around the exact value of pi over 4, getting closer with each step. The trouble with this series is that it converges very slowly. To get even 2 decimal places of pi, you need to add several hundred terms. But Madhava and his students developed convergence acceleration methods, corrections that yielded far greater accuracy from fewer terms. Using these refined series, the Kerala school computed pi to 11 decimal places. 11 places, in the 15th century, long before the era of mechanical computing machines.
For comparison, Archimedes achieved about 2 decimal places, Su Chongzhe 7. Madhava's 11 places represent a leap made possible precisely by infinite series. But Madhava and his followers did not stop at arctangent. They developed expansions that we recognize today as Taylor series, one of the most important tools of advanced calculus. A Taylor series allows you to represent virtually any well-behaved function as an infinite sum of power terms. In other words, to reduce a complicated function to an infinite polynomial. This is an incredibly powerful method, and the Kerala school commanded its basics centuries before Taylor. They also worked with what we would call derivatives of trigonometric functions, or at least with concepts equivalent to derivatives. They understood something deep about the connection between infinite processes and exact values. And here, history poses a puzzle that historians still debate. Did the Kerala school's knowledge reach Europe? The facts are these. Kerala was a major trading hub. The Malabar coast was one of the chief centers of the spice trade, and ships from Arabia, China, Southeast Asia, and, starting in the late 15th century, Europe regularly called at Keralan ports. Portuguese ships began arriving on the Malabar coast around 1500. Vasco da Gama reached Calicut in 1498. Jesuit missionaries were active in the region and are documented to have collected and sent manuscripts, including mathematical and astronomical ones, back to Europe. The chronology allows for transmission. The Kerala school was active in the 15th and 16th centuries. European travelers and missionaries were present in Kerala in the 16th century, and European mathematicians began working with infinite series in the 17th. The historian of mathematics, George Gevagese Joseph, author of The Crest of the Peacock, has argued vigorously for possible transmission. Other historians, Kim Plofker, David Pingree, are more skeptical. But no direct evidence of transmission has been found. Not a single document in which a European mathematician cited an Indian source. Not a single translation
that can be dated to the right period. As far as we can tell from the available documentary evidence, the Kerala school's discoveries remained unknown outside Kerala until 1835, when a British researcher named Charles Matthew Wish wrote about them, by which point Newton and Leibniz had long since finished their work. So the most likely picture is this. Europe and India arrived at many of the same ideas entirely independently, through entirely different paths. And if that is the case, it is yet more evidence that the ideas of calculus were no accident. They were something waiting to be discovered at every end of the earth, in every culture that asked the right questions.
But then comes the next question, and it is crucially important for our story. If the Kerala school had infinite series, Taylor-like expansions, outstanding approximations of pi, and concepts equivalent to derivatives, why is Madhava not considered the creator of calculus? Why does that title belong to Newton and Leibniz? The answer to this question is the key to everything that follows, because it explains what exactly turned calculus from a collection of clever tricks into a universal machine. The Kerala school possessed many components, but they did not connect them into a unified theory. They did not formulate the fundamental theorem of calculus, the foundational discovery that differentiation and integration are inverse operations. They did not develop a systematic notation, a language of symbols that would let any trained person apply the method to arbitrary problems. They did not create what you might call an algorithm, a step-by-step recipe that you can teach, that a student can learn, and that the student can then apply to any function, any curve, any problem about motion. They had brilliant fragments. Newton and Leibniz, or more precisely, the European mathematical tradition that they culminated, assembled all the fragments into a working machine. An analogy helps. Imagine that different people in different workshops built wheels, pedals, a frame, a chain, and handlebars. Each is a master craftsman. Each created a wonderful component. But a bicycle appears only when someone connects all the parts into a single working assembly and shows that the pedals turn the wheel through the chain, the handlebars steer, and the whole thing lets you ride. The Kerala school built several key parts: infinite series, proto-derivatives, approximations. Newton and Leibniz assembled the bicycle. The historian of mathematics, Victor Katz, put it this way: the Kerala school was unable to bring together its many different ideas under the two unifying themes of the derivative and the integral, show the connection between them, and turn calculus into the great problem-solving tool it is today. There is another factor worth mentioning. The Kerala school worked in relative isolation. It had no broad scientific communication network, no printing press, no university system to broadcast discoveries to the world. Ideas stayed within a tight circle of students and followers, and, as far as we can tell, did not spread beyond that circle. Europe, by the 17th century, had a developed infrastructure for scientific exchange: academies, journals, active correspondence among scholars in different countries. When Leibniz published his paper, it was available to mathematicians from London to St. Petersburg. When the Bernoulli brothers extended his methods, their results spread instantly through the entire scientific community. Context, infrastructure, institutions, the means of communication, matters no less than the genius of any single person. This is a significant difference. But it should not overshadow the astonishing fact. Across millennia, through multiple independent civilizations, people kept arriving at the same ideas, because those ideas are the natural way to think about change, area, and infinite processes. The ideas, it seems, were always nearby. They were waiting. And now, Europe, the 17th century, the place where all the threads will finally intertwine. The place where scattered brushes with infinity
will become a system capable of describing the motion of planets, the flight of a cannonball, the vibration of a string, and the shape of a bridge arch.
Here, a whole constellation of minds enters the stage, each adding a piece to the mosaic. And two of them will ultimately lay claim to the entire picture. By the start of the 17th century, European mathematics had come a long way back. Arab scholars had preserved, translated, and extended the Greek heritage. Through Spain, through Italy, through the Crusades and trade routes, that knowledge returned to Europe. Algebra, the very word comes from the Arabic al-jabr, had become a full-fledged discipline. European universities were up and running. Printing presses had appeared and begun to mass-produce books. Gutenberg printed his Bible around 1455, and within half a century, print shops had spread across Europe. Books were no longer a luxury available only to monasteries and courts. A scholar in Krakow could read what a scholar in Florence had written within months, not decades. The scientific community, loose, still without formal institutions, had come into being as a real network for exchanging ideas. This matters for our story because calculus is not the product of a lone genius, though geniuses certainly played a key role. Calculus is the culmination of a rising wave of ideas passed from one mathematician to another through books, letters, personal meetings, and apprenticeship. Descartes read Viet, Fermat knew Descartes' work, Barrow taught Newton, Huygens taught Leibniz. Without this chain of transmission, without the infrastructure of communication, there would have been no calculus. And the problems that most preoccupied the scientists of that time were exactly the problems calculus would solve. The first set of problems was about motion. How do planets move? Copernicus in 1543 had shown that the Earth orbits the Sun rather than the other way around. Tycho Brahe, the Danish astronomer, spent decades measuring planetary positions with unprecedented precision. By hand, without a telescope, using enormous angular instruments at his island observatory of Uraniborg. His assistant, Johannes Kepler, gaining access to Brahe's data after his death, spent years of grueling calculations and finally derived 3 laws of planetary motion. The first law: planets move in ellipses, not circles, with the Sun at one focus. The second: the radius vector from the Sun to a planet sweeps out equal areas in equal intervals of time, meaning a planet speeds up when it is near the Sun and slows down when it is far away. The third: the square of the orbital period is proportional to the cube of the semi-major axis. But describing motion is one thing, explaining it is something else entirely. Kepler had found the patterns, but he could not explain why planets obey these particular laws. What force governs their trajectories? Answering that question required mathematical tools capable of describing continuous change. Velocity that shifts from instant to instant. Acceleration that depends on distance. Curves whose slope varies continuously. The second set of problems was about the geometry of curves. What is the area under this curve? What is the volume of this solid of revolution? At what point does the curve reach its maximum or minimum? At what angle does it rise at a given point? What is the slope of the tangent line? These were not abstract questions. Engineering calculations, optical research, the shape of lenses, navigation, trajectories of ships and projectiles, and architecture, the shape of arches and domes, all depended on them. Both sets of problems, motion and geometry, demanded the same thing: mathematics capable of handling continuous change. Curves that keep turning, speeds that keep shifting, areas bounded not by straight lines, but by smooth curves. The existing mathematics, arithmetic, Euclidean geometry, algebra, could handle the constant, the linear, the straight. But the world described by Kepler and Galileo was not straight. It was curved. The tools for working with a curved world did not yet exist. They had to be created. And the first step was taken by a man usually thought of as a philosopher rather than a mathematician. René Descartes, in the 1630s, united algebra with geometry. Descartes is a figure of colossal stature, a philosopher famous for the phrase, cogito ergo sum, I think, therefore I am. He upended European philosophy by placing doubt at the center of knowledge. But for our story, his mathematical work matters more. It was published in 1637 as an appendix to his philosophical treatise, Discourse on the Method. Before Descartes, algebra and geometry were two separate worlds, two parallel traditions that barely intersected. Geometry dealt with shapes, circles, lines, parabolas, but in a purely visual, spatial way. You could draw a circle, but could not write down its formula. Algebra worked with equations. X squared plus y squared equals r squared, but without any connection to a picture. You could solve an equation, but could not see the solution. Descartes showed that every equation corresponds to a curve, and every curve to an equation. He introduced the coordinate system, the familiar grid with x and y axes that we now call the Cartesian plane. And through it, any geometric problem could be restated as an algebraic one, and vice versa. Consider the scale of this step. Before Descartes, a parabola was a shape you saw when you threw a ball. After Descartes, a parabola was y equals x squared. Before Descartes, a circle was a shape drawn with a compass. After Descartes, a circle was x squared plus y squared equals r squared. Before Descartes, an ellipse was a slice of a cone. After Descartes, an ellipse was x squared over a squared plus y squared over b squared equals 1. Every curve becomes an equation. Every equation becomes a curve. Two great branches of mathematics, geometry and algebra, merge into one. This unification, which we take for granted today, in school, algebra and geometry are interwoven so tightly that it is hard to recall they once existed separately, was a genuine revolution in its time. Why was this so important for the history of calculus? Because now, instead of constructing a clever geometric proof for each curve separately, as Archimedes had to do, you could write the curve as an equation and work with algebra. Algebra allows generalization. Algebra allows recipes. A method that works for one equation can work for an entire class of equations. This is exactly what Archimedes lacked. He solved each problem individually because he had no way to translate geometry into a language suited for generalization. The Cartesian coordinate system is a bridge between shape and formula. And without that bridge, calculus in its modern form would have been impossible. Working at the same time as Descartes, literally in the same years, was another Frenchman, Pierre de Fermat. Yes, the same Fermat whose last theorem remained unproven for more than 350 years until Andrew Wiles solved it in 1995. But Fermat was not only a number theorist. He worked on problems that today we would classify as differential calculus. Fermat developed methods for finding the maxima and minima of functions and for constructing tangent lines to curves. His approach was called the method of adequality, and it deserves a detailed description because in it lies a protoform of differentiation. Here is what Fermat did. Suppose you are looking for the maximum of a function f of x. At the maximum, the curve levels out. If you shift slightly to the right or left of the maximum, the function's value barely changes. More precisely, the value of f of x at the maximum is approximately equal to f of x plus e, where e is a small increment. Fermat wrote, f of x is approximately equal to f of x plus e. He substituted, expanded, simplified, subtracted f of x from both sides, divided by e, and obtained an equation still containing e. Then he set e equal to 0 and solved the resulting equation for x. Let us do this for f of x equals x times the quantity a minus x, where a is a fixed constant. This is an upside-down parabola. F of x equals ax minus x squared. F of x plus e equals a times x plus e minus x plus e squared, which equals ax plus ae minus x squared minus 2xe minus e squared. Setting them approximately equal, ax minus x squared is approximately ax plus ae minus x squared minus 2xe minus e squared. Simplifying, 0 is approximately ae minus 2xe minus e squared. Dividing by e, 0 is approximately a minus 2x minus e. Setting e equal to 0. A minus 2x equals 0, so x equals a over 2. The maximum of x times the quantity a minus x occurs at x equals a over 2. The correct answer. And if you look closely, you will see that Fermat essentially computed the derivative and set it equal to 0. Exactly what we do today. His add equality is the precursor of our limit. His e that is then set to 0 is the precursor of our h approaching 0. Fermat also worked on problems we would today classify as integration, finding areas under curves. He could compute the area under the parabola y equals x to the nth power for integer values of n, using partitions into rectangles with geometrically increasing widths, a trick that reduced the sum of infinitely many rectangles to a geometric series that could be summed.
But, and here is the same pattern we saw with Archimedes and Madhava, Fermat did not connect the two directions. He found slopes. He found areas. He did not notice that these two operations are mirror images of each other. Or at least, he did not formalize the observation. Around 1635 to 1647, the Italian mathematician Bonaventura Cavalieri published a work he called The Method of Indivisibles. His idea was conceptually simple and astonishingly powerful. He proposed thinking of an area as a collection of infinitely many, infinitely thin lines standing side by side, like pages in a book, and a volume as a collection of infinitely many, infinitely thin slabs stacked like pancakes. This is the same idea Archimedes used in his secret method, and the idea Leibniz would place at the center of his approach. Slicing into infinitely thin pieces and adding them up. That is integration. Cavalieri's method included a remarkable principle that today bears his name, Cavalieri's principle. If two solids have the same cross-sectional area at every height, then they have the same volume. It sounds obvious, but non-trivial results follow. For example, a tilted cylinder, like the Leaning Tower of Pisa, has the same volume as an upright cylinder of the same height with the same base, because at every height the cross-section is the same. Cavalieri could not rigorously justify his approach. What does infinitely thin line mean? A line has no area. How can you add infinitely many zeros and get something non-zero? These questions haunted mathematicians, and the rigorous answer would not come until the 19th century. Pascal, working around the same time, defended Cavalieri.
When we speak of an infinite number of lines, we mean a finite number of rectangles made on those lines, and such an expression is harmless, for the result is the same.
Pascal was intuitively groping toward what Riemann would formalize 200 years later. Not infinitely thin lines, but the limit of a sum of finite rectangles whose width approaches zero. And finally, Isaac Barrow. Barrow was a professor of mathematics at Cambridge and, crucially for our story, Newton's teacher. Barrow occupies a unique position in the history of calculus. He was the first person who explicitly saw and proved that finding areas, integration, and finding slopes, differentiation, are inverse operations. He saw the fundamental theorem of calculus. He stated it in geometric form. If you have a curve, and you construct another curve that at each point shows the area under the first one, from the starting point to that point, then the slope of the second curve at any point equals the value of the first curve at that point. In modern terms, the derivative of the integral equals the integrand. Barrow proved it, geometrically, through the construction of tangent lines. He held it in his hands. The theorem that links differentiation and integration. But he did not take the next step. He did not turn his discovery into a computational algorithm. He did not say, "And now, here is how you use this to find the area under any curve. Find the antiderivative and plug in the endpoints." He had a deep geometric observation, clothed in geometric language and proved by geometric means. He did not build a machine out of it, a recipe that could be taught, that a student could follow, that would work automatically for any function. The historian of mathematics, Margaret Barron, noted that Barrow was one step from calculus. But that step, from geometric intuition to algorithmic method, turned out to be enormous. It would be taken by Newton and Leibniz. That next step, turning a collection of deep but scattered ideas into a single, universal, working system, was to be made by two people, each arriving at it independently, from different directions, within a single decade. Think about where we are now in our story. 4,000 years of development. The Egyptians found a formula whose derivation requires an integral. The Babylonians integrated Jupiter's velocity. Archimedes developed the method of exhaustion. Liu Hui reinvented it in China. Ibn al-Haytham advanced sums of powers. Madhava discovered infinite series. Descartes united algebra and geometry. Fermat effectively differentiated. Cavalieri integrated with indivisibles. Barrow saw the fundamental theorem. All the pieces of the mosaic are on the table. All that remains is to assemble them into a picture. And the story of how that happened, or rather, the story of what happened afterward, became one of the most gripping and most bitter episodes in the annals of science. One of these men was sitting in the family estate in the English countryside, hiding from the plague. He was 22 years old. The other, a cosmopolitan polymath, diplomat, and philosopher, had not even begun to study mathematics seriously at that point. They were separated by 4 years of age, the English Channel, and utterly different ways of thinking about the world. Let us start with the one who came first, with a farmer's son and the plague. Isaac Newton was born on December 25, 1642, by the Julian calendar, January 4th, 1643, by the Gregorian, in the village of Woolsthorpe, Lincolnshire, England. He was born prematurely, so small that according to his mother, He could have fit inside a quart mug, and no one expected him to survive. His father, an illiterate farmer, had died 3 months before his birth.
When Newton was 3, his mother remarried a well-off clergyman named Barnabas Smith and moved in with her new husband in a neighboring village, leaving little Isaac in the care of his grandmother. Newton hated his stepfather. He recorded it in his diary, listing his sins, threatening my father and mother Smith to burn them and the house over them. He was about 10 years old at the time. This childhood, marked by abandonment and anger, left its stamp on his entire life. Newton never learned to trust people, never learned to accept criticism without fury, never learned to share. By most accounts, at school, the King's School in Grantham, Newton did not stand out at first. His mother pulled him out at 14 to run the farm. The family needed working hands. Newton turned out to be a terrible farmer. He forgot about the sheep, lost livestock, let pigs wander onto neighbors' fields.
Instead of watching the flock, he sat under a tree, reading or building mechanical models, watermills, sundials, a cart you could propel by sitting inside and cranking a lever. Eventually, his schoolmaster Henry Stokes and his uncle William Ayscough persuaded his mother to let him go back to school, and from there to Cambridge University. Stokes reportedly wept during his farewell speech and called Newton the best student he had ever seen. Newton entered Trinity College, Cambridge in 1661. He was a so-called subsizar, a student who paid for his education by serving wealthier students. He cleaned rooms for well-off classmates, emptied chamber pots, served meals. Socially, he was at the bottom of the university hierarchy. By all indications, he had very few friends. But in the Cambridge Library, Newton found what would change his life. He discovered that the university's official curriculum, Aristotelian scholastic philosophy, was a century behind modern science, and he began to read on his own. He picked up Descartes' geometry, and at first understood almost nothing. He went back to the beginning, reread, understood nothing again, went back a third time and a fourth, and gradually, through a persistence bordering on obsession, he not only understood Descartes, but moved beyond him. He read the works of John Wallis, who in his Arithmetica Infinitorum had extended Cavalieri's ideas and worked with infinite series. He studied the works of Barrow, his future teacher, on geometry and optics. He devoured mathematics at such speed that within 2 years, from 1663 to 1665, he surpassed everything known to his contemporaries. And then the plague struck. In 1665, the Great Plague reached Cambridge. It was the last major outbreak of bubonic plague in England, a disease that killed up to 40% of those infected. In London alone, roughly 100,000 people died, a quarter of the city's population. The university closed and students scattered to their homes. Newton returned to Woolsthorpe, to the very family home where he had been born. He was 22 years old. Behind him, 2 years of intense, self-directed reading and thinking. Ahead, 18 months of forced solitude. What happened next is sometimes called the Annus Mirabilis, the miraculous year, though it was closer to a year and a half. And this period is perhaps the most astonishing burst of individual genius in the history of science. During this time, sitting in a farmhouse in the countryside, a 22-year-old who just a few years earlier could not keep track of sheep did the following. Invented calculus, discovered the laws of motion, developed the theory of universal gravitation, and laid the foundations of his work on optics. Think about that. One person, 22 years old, during a plague.
In the countryside,
And in 18 months, he created a mathematical tool, described the fundamental laws of physics, and explained why the planets move the way they do. The historian of science Richard Westphal, author of the most detailed biography of Newton, wrote that if Newton had lived only 26 years, if he had died young, like Galois, he would still have gone down in history as one of the greatest mathematicians of all time. The scale of what he accomplished during those 18 months in Woolsthorpe has no parallel. Neither before nor since has any single person done so much in so short a time. Of course, he did not produce all of this in finished, polished form. The ideas needed refinement, the notation was raw, many results were jotted in notebooks that only he could read. Publication would come decades later. The Principia Mathematica, the crowning work of his life, would not appear until 1687, 22 years after the plague period.
But the core, the key ideas, were formed right there in Woolsthorpe, between the sheep he still forgot to count and the apple orchard that may indeed have hinted at something about gravity. After returning to Cambridge when the plague subsided, Newton became Barrow's protégé, and then, when Barrow voluntarily gave up his chair, the Lucasian Professor of Mathematics at 26. But he was in no hurry to make his calculus public. It circulated in manuscripts, in letters, in private conversations, but not in print. Newton called his method the method of fluxions. The word fluxion in Newton's terminology meant rate of change, essentially what we now call the derivative. Newton thought of curves as trajectories traced by moving points. If a point moves across a plane, tracing a curve, then at every moment it has a velocity, a direction, and a speed. This instantaneous velocity, the fluxion, is the key quantity.
Finding the fluxion means finding how fast something is changing at a given moment. Newton's approach was deeply physical. He thought in terms of motion and time. A curve is not just a figure on paper, but a trail left by a moving object. The derivative is not an abstract mathematical object, but the instantaneous speed of that object. The integral is not area under a curve in a geometric sense, but the total distance travelled over a given time. This physical intuition was immensely powerful. It let Newton see the connection between calculus and mechanics, a connection that would become the foundation of all classical physics. Newton's second law, F equals m times a, force equals mass times acceleration, is, when you think about it, a statement about the second derivative. Acceleration is the rate of change of velocity, which is the derivative of position.
The law of gravitation, involving the inverse square of distance, leads to a differential equation whose solution is an elliptical orbit. This is how Newton explained Kepler's laws. He showed that they follow mathematically from the law of gravitation through calculus. Kepler had established the laws empirically, by observing planetary orbits and finding patterns. But he could not explain why planets obey those laws. Newton gave the answer. Because between any two bodies there acts a force of attraction proportional to the product of their masses and inversely proportional to the square of the distance between them. From this single assumption, through calculus, all three of Kepler's laws follow: elliptical orbits, equal areas in equal times, and the relationship between period and orbital radius. This was perhaps the first time in history that mathematics did not merely describe nature but explained it. To describe is to say, planets move in ellipses. To explain is to say, planets move in ellipses because gravity acts as the inverse square of distance, and here is the mathematical proof. Calculus made explanation possible. But let us return to what Newton was actually doing when he invented calculus. To understand that, you need to understand how the derivative works. And this is a good moment to pause and dig into it, because the derivative is the first of the two fundamental operations of calculus, and if you grasp it, the second half will fall into place much more easily. Here is the question everything starts with. How fast is something changing? Imagine you are in a car. Over the last hour you covered 60 miles, average speed 60 miles per hour, distance divided by time, easy. But here is a subtler question. What was your speed at the exact moment you passed the red sign on the shoulder? You were not going the same speed the whole time. You accelerated, braked, maybe sat at a traffic light.
The average speed over the hour is a blended number that hides all those fluctuations. But you need not the average, but the instantaneous speed, the one the speedometer shows. The speed at this moment, at this point in space, in this fraction of a second. And here is the problem. How do you define speed at a single instant? Speed is distance divided by time. But in a single instant, there is no distance and no interval of time. There are no 2 points between which you can measure a difference. You have 1 point, and that is it. You need to measure motion in an instant, but an instant, by definition, contains no motion. This, by the way, is exactly the paradox of Zeno's arrow, which we encountered in the chapter on Archimedes. The arrow at each instant is motionless. It occupies a definite position, and at that position there is no motion. How do you define the speed of something that at this moment is motionless?
Zeno argued it was impossible, and therefore, motion is an illusion. Newton and Leibniz, independently, found the answer Zeno had been looking for 21 centuries. Newton approached it this way. Suppose you want to know the instantaneous speed at time t. Take another moment close to t, say t plus h, where h is a small interval. Compute how far you travelled during that interval h. Divide by h. You get the average speed over a short interval. Now shrink h. The average speed over a shorter interval is a more accurate estimate of the instantaneous speed. Shrink h again. Even more accurate. Keep shrinking h, driving it towards zero. In the limit, as h approaches zero, the average speed approaches the instantaneous speed. This is the derivative, the limit of the ratio of the change in the function to the change in the argument, as the change in the argument approaches zero. Let us write it a bit more formally, because the statement is beautiful and worth seeing. Suppose you have a function f, a rule that assigns to every number x another number f of x. The derivative of f at the point x is the limit of the expression f of x plus h minus f of x, all divided by h as h approaches zero. Let us unpack that. F of x is the value of the function at the point x. F of x plus h is the value at a point shifted slightly to the right by h. The difference, f of x plus h minus f of x, is the rise, the vertical change in the function. Divide by h, the run, the horizontal change in the argument. You get the slope of the secant line, the straight line drawn through 2 points on the graph. A secant is a line that cuts through the curve at 2 points. A tangent is a line that merely touches the curve at 1 point, following its direction. The secant is a rough approximation of the tangent. The closer together the 2 points through which the secant is drawn, the more accurately it approximates the tangent.
As h shrinks, the 2 points move closer together. The secant rotates, like a compass needle, homing in on the true direction of the curve. In the limit, as h approaches zero and the points merge, the secant becomes the tangent. The slope of the tangent is the derivative. Here is a geometric picture. Imagine looking at a mountain. From a distance, you see the overall shape: a gentle rise, a steep slope, a flat summit. But the derivative is not the overall shape. The derivative is the slope of the mountain right under your feet. If you are standing on a steep section, the derivative is large. If on a flat section, small. If on the summit, 0. The derivative is a local property. It describes the function's behavior at a single point, ignoring everything else. Let us compute an example, because one thing is to describe the idea in words, and quite another to see it work on actual numbers. Take the simplest non-linear function, f of x equals x squared. This is the parabola, that familiar U-shaped curve. We want to find how fast it is growing at the point x equals 3. Substitute into the definition of the derivative. F of 3 plus h equals 3 plus h squared, which is 9 plus 6h plus h squared. F of 3 equals 9. The difference, f of 3 plus h minus f of 3, equals 9 plus 6h plus h squared minus 9, which is 6h plus h squared. Divide by h. 6h plus h squared over h equals 6 plus h. Now take the limit as h goes to 0. The limit of 6 plus h is 6. The derivative of x squared at the point x equals 3 is 6. The function at that point is growing at a rate of 6, meaning if you shift slightly to the right of 3, the function's value increases roughly 6 times as much as your shift. Now let us do the same for an arbitrary point x, not just for 3. F of x plus h equals x plus h squared, which is x squared plus 2xh plus h squared. F of x equals x squared.
Difference, 2 times h plus h squared. Divide by h, 2x plus h. Limit as h goes to 0, 2x. The derivative of x squared is 2x. Everywhere, for any x. At x equals 3, it is 6. At x equals 5, it is 10. At x equals 0, it is 0. The parabola at its vertex is flat. The tangent line is horizontal. We have just performed the first operation of calculus, differentiation. We took a function, f of x equals x squared, applied a specific procedure to it, the limit definition of the derivative, and obtained a new function, f prime of x equals 2x. This new function tells us how fast the original function is growing at every point. Pause for a moment and think about what we just did. We started with a geometric object, a parabola, applied an algebraic procedure, expanded brackets, cancelled, took a limit, and got the answer to a physical question. How fast is the parabola rising at each point? 3 worlds, geometry, algebra, physics, converging in a single operation. This is exactly why calculus is so powerful. It links shape, formula, and motion. If you think about it, the result f prime of x equals 2x contains a lot of information. It says that at x equals 0, the parabola is flat, derivative is 0, the tangent is horizontal. That is the bottom of the parabola, its vertex. For x greater than 0, the derivative is positive, the parabola is rising. For x less than 0, the derivative is negative, the parabola is falling. The farther from 0, the faster the rise or fall. At x equals 10, the derivative is 20. At x equals 100, it is 200. The parabola accelerates, and the rate of acceleration is described by the linear function 2x. Newton did exactly this, but not only for x squared. He worked with polynomials, trigonometric functions, fractions, roots. And he discovered patterns,
regularities that allowed him to find derivatives without going through the cumbersome limit procedure every time. The most important of these patterns is the power rule. The derivative of x to the n equals n times x to the n minus 1. You take the exponent, bring it down as a multiplier, and reduce the power by 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of x to the fourth is 4x cubed. The derivative of x to the fifth is 5x to the fourth. See the pattern? The exponent comes down, the power decreases by 1 every time. And the beauty is that it works, provably, rigorously, for any exponent. This rule holds for any exponent: integer, fractional, negative, irrational. The derivative of the square root of x, which is x to the 1/2, is 1/2 times x to the minus 1/2, or 1/2 times the square root of x. The derivative of 1/x, which is x to the minus 1, is minus 1 times x to the minus 2, or minus 1/x squared. The derivative of x to the pi is pi times x to the pi minus 1. The power rule is an enormous simplification. Instead of going through the limit every time, expanding binomials, cancelling, sending h to 0, you just apply the rule. Bring down the exponent, reduce by 1. 3 seconds. What used to take a page of computation collapses to an instant operation. And here is the heart of what Newton and Leibniz did that their predecessors did not. Archimedes could compute the area of a parabola, but each new shape required a new proof. Fermat could find the maximum of a particular function, but each function called for a separate trick. Newton and Leibniz created a system of rules, an algorithm, a recipe that can be learned and applied to any function. The power rule, the product rule, the quotient rule, the chain rule. A toolkit that, like building blocks, can be combined to differentiate arbitrarily complex expressions. The product rule. The derivative of the product of two functions f and g equals f prime times g plus f times g prime. You differentiate the first, leaving the second alone. Then differentiate the second, leaving the first alone, and add. Where does this rule come from? Imagine a rectangle with sides f and g. Its area is f times g. Now both sides grow slightly. F becomes f plus delta f. G becomes g plus delta g. The new area, f plus delta f times g plus delta g, equals fg plus f times delta g plus g times delta f plus delta f times delta g. The change in area, f times delta g plus g times delta f plus delta f times delta g. The last term is the product of two small quantities, small squared, and in the limit it vanishes. What remains, f times delta g plus g times delta f. Divide by delta x and you get f times g prime plus g times f prime. The product rule. A beautiful example of geometric intuition yielding an algebraic result. The chain rule, the rule for compositions of functions, is perhaps the most important of all. If you have one function nested inside another, for example, sine of x squared, where sine is wrapped around x squared, then the derivative of the composite is computed link by link. First, differentiate the outer function, plugging the inner function in as the argument, Then multiply by the derivative of the inner function. For sine of x squared, the outer function is sine, its derivative is cosine. The inner function is x squared, its derivative is 2x. Result, cosine of x squared times 2x. Let us make sure the chain rule is clear, because it is one of the most important rules in all of calculus, and its significance extends far beyond pure mathematics. Imagine this situation. Air temperature affects air density. Air density affects the lift on a wing. You want to know, how does temperature affect lift? The answer? Through a chain. A change in temperature causes a change in density at a certain rate. A change in density causes a change in lift at a different rate. The overall effect is the product of these two rates. Temperature to density to lift. Each arrow is a derivative. The overall effect is the product of the derivatives. Here is what the chain rule says. If y depends on u and u depends on x, then the rate of change of y with respect to x equals the product of the rate of change of y with respect to u and the rate of change of u with respect to x. In Leibniz's notation, dy over dx equals dy over du times du over dx. If the chain is longer, y depends on v, v on u, u on x, then dy over dx equals dy over dv times dv over du times du over dx. The product of three derivatives. 4 links, 4 factors. 10 links, 10 factors. The chain rule generalizes to a chain of any length. 350 years later, exactly this property, the ability to thread a derivative through a long chain of nested functions, would turn out to be the mathematical engine of the most powerful machine learning algorithm in existence today.
A neural network is, at its core, a very long chain of nested functions. Input to first layer to second layer to output. Training that network requires computing the derivative of the error with respect to every parameter in every layer. That is, threading the derivative through the entire chain. The Leibniz chain rule is the foundation of this process. Remember it. We will return to it at the end of our story. Newton developed all of this. The method of fluxions, the rules of differentiation, the connection to physics. In 1665 and 66, he wrote down his results, and then he did not publish them. He showed his work to a small circle of mathematicians he trusted. His ideas were implicitly present in his great work, The Mathematical Principles of Natural Philosophy, Philosophiae Naturalis Principia Mathematica, published in 1687. The Principia is one of the most important scientific books in all of human history. In it, Newton formulated the 3 laws of motion and the law of universal gravitation, derived planetary orbits, explained the tides, predicted the shape of the Earth, flattened at the poles, and laid the foundation for all of classical physics. But, and this is important for our story, Newton deliberately hid calculus from the Principia. The book is written in a geometric style, in the tradition of Euclid. Theorems, proofs, diagrams. Newton apparently first obtained his results using his method of fluxions, and then translated them into the language of geometry for publication. Why? Partly because geometric proofs were considered more rigorous, partly because he did not want to reveal his method. The calculus work itself, the method of fluxions as such, Newton published only posthumously, in 1736, 9 years after his death and 70 years after he developed it. Why? Newton was pathologically secretive and pathologically afraid of disputes. Earlier, he had gotten embroiled in an unpleasant controversy over his work on optics. Robert Hooke, the curator of experiments at the Royal Society, had criticized his theory of light, and Newton took it extremely hard. He wrote,
I blame my own imprudence for parting with so substantial a blessing as my quiet to run after a shadow. From that point on, he loathed public discussions, loathed the very possibility that someone might challenge his work, and his solution was simply not to publish. There is irony in the fact that Newton, the greatest mind of his time, and possibly of any time, was so emotionally vulnerable that he preferred to keep his discoveries in a desk drawer rather than expose himself to criticism. He recorded results in notebooks that only he read. He hinted at his methods in letters, enough to later claim priority, but not enough for anyone to reproduce his work.
He even encrypted descriptions of his results as anagrams, scrambling the letters of a Latin sentence, describing a theorem, and sending the anagram as proof of priority that could be unscrambled if needed. This combination of supreme genius and supreme anxiety is one of the strangest human stories in science, and it laid the groundwork for the catastrophe that would unfold in the following decades. Because Newton's refusal to publish created a situation in which his priority remained unproven, unconfirmed, existing only in private notes and the recollections of a few trusted confidants. Newton was a man of enormous extremes. Besides mathematics and physics, he spent decades on alchemy, attempts to transmute base metals into gold, and wrote more on that subject than on mathematics and physics combined. He wrote extensive theological tracts in which he secretly denied the doctrine of the Trinity, a heresy that, had it become public, would have destroyed his career. He devoted years to chronological analysis of the Bible, trying to compute the precise date of the end of the world. He was, by any standard, a strange man, brilliant but isolated, suspicious, vindictive, incapable of maintaining normal human relationships. And when, meanwhile in Germany, a completely different person was arriving at the very same ideas, a person who differed from Newton in every way, a collision became inevitable. Where Newton was withdrawn, this man was sociable. Where Newton hid his discoveries, this man rushed to publish. Where Newton thought physically, through motion and speed, this man thought geometrically, through shapes and tangents. And he created the notation that the entire world still uses today. Gottfried Wilhelm Leibniz was born on July 1st, 1646, in Leipzig, 4 years after Newton. His father, a professor of moral philosophy at the University of Leipzig, died when Leibniz was 6. His mother raised him alone. Even as a child, Leibniz showed a remarkable capacity for learning. He taught himself Latin by the age of 12, reading books from his father's library. By 15, he had enrolled at the University of Leipzig. By 21, he had earned a doctoral degree in law. If Newton is the story of an obsessive loner, a recluse who worked in isolation and hid his discoveries, then Leibniz is the story of a universal mind, a man who wanted to know and do everything and share it all. Leibniz was a polymath in the most extreme sense of the word. A philosopher, one of the greatest in the history of Western thought, author of the Monadology and the Theodicy, creator of the concept of the best of all possible worlds, which Voltaire would later satirize in Candide. A diplomat, he served at the courts of several German princes and was actively involved in political negotiations to reunify the Protestant and Catholic churches. A jurist, his doctoral dissertation was in law. A historian, he wrote a history of the House of Welf, the ruling dynasty of Hanover, traveling through archives across Europe. A logician, his work on formal logic and symbolic representation of reasoning was 2 centuries ahead of its time, anticipating Boole and Frege. An inventor, he designed one of the first mechanical calculating machines capable of performing all 4 arithmetic operations. A linguist, a librarian, a mining engineer, a scholar of Chinese philosophy. Newton was the fox who knew one great thing.
Leibniz was the hedgehog who knew many things, or rather, he was that rare person who was both fox and hedgehog at once. And a mathematician. Though he came to mathematics relatively late, he did not begin serious work until he was past 25. Before that, mathematics was just one of his many interests, and not the main one. The turning point came in 1672, when Leibniz found himself in Paris on a diplomatic mission. He was trying to persuade Louis XIV to direct France's military energy toward conquering Egypt instead of invading Holland, a plan that obviously did not work, but shows the scale of Leibniz's ambitions. There he met the Dutch mathematician and physicist Christian Huygens, one of the leading scientists of Europe, a man who, among other things, had discovered the rings of Saturn and its moon Titan, invented the pendulum clock, contributed to the wave theory of light, and written one of the first treatises on probability theory. Huygens quickly recognized the young Leibniz's brilliance, and simultaneously realized that his mathematical education lagged catastrophically behind his abilities. Leibniz was a dazzling thinker, but his knowledge of mathematics was at the level of a talented amateur, no more. Huygens essentially handed him a reading list. Read Pascal, read Descartes, read Gregory of Saint Vincent. That is what you need to understand what we are talking about here. Leibniz caught up astonishingly fast. He described his learning process in his diary, and it makes for gripping reading. He read Pascal, Descartes, Cavalieri, Gregory of Saint Vincent. He studied problems posed to him by Huygens and others, and gradually, over the course of a few years, he not only mastered the entire body of contemporary mathematics, but began to see in it a structure that others had missed. Leibniz thought on a grand scale. He dreamed of creating a characteristica universalis, a universal language of symbols in which any thought, any argument, any problem could be written, and a calculus ratiocinator, a machine for automatic reasoning that would settle disputes not by shouting but by computing. Let us calculate. This dream, fantastical for the 17th century, was in a sense realized in the 20th, in formal logic, in computer science, in machine-assisted theorem proving. And his work on calculus was part of this larger project, the creation of a symbolic language for describing change. That is why Leibniz took notation so seriously. For him, symbols were not mere labels but tools for thinking. Unlike Newton, whose instinct was to think of curves as trails left by moving points in time, Leibniz was drawn to the geometric problem of tangent lines and areas. He thought not in terms of speeds and accelerations, but in terms of infinitely small differences, differentials. What is a differential? Imagine a function y equals f of x. If x changes by a tiny amount dx, then y changes by a tiny amount dy. Leibniz thought of dx and dy as infinitesimally small increments, quantities smaller than any finite number yet not equal to zero.
The ratio dy over dx is the slope of the tangent, the derivative. Where Newton saw the velocity of a moving point and asked, "How fast is it moving?" Leibniz saw two infinitely close values of a function and asked, "How do they relate?" Newton thought dynamically, through time and motion. Leibniz thought statically, through infinitely small differences, frozen at a single moment. This conceptual gap between the two approaches, physical, Newton, and geometric, Leibniz, is more than a historical footnote. It is deep and interesting. Both approaches lead to the same mathematics, the same formulas, the same answers. But the way of thinking about them differs, and that difference still shows up in how calculus is taught to different audiences. Physicists typically find Newton's approach more natural, change over time, velocity, acceleration. Mathematicians and engineers often prefer Leibniz's, infinitesimal increments, ratios of differentials. By October of 1675, Leibniz had developed the core of his differential calculus. And then he did something Newton had not.
he introduced brilliant notation. In 1675, Leibniz wrote down the symbol we use today for the integral, an elongated letter S from the Latin word summa, meaning sum. He introduced the letter D for differential, the infinitely small increment. Thus, dx and dy were born, infinitely small changes in the variables x and y. And he wrote the derivative as dy over dx, the ratio of the infinitely small change in y to the infinitely small change in x. On October 29th, 1675, the date is known from his diaries, Leibniz first wrote the symbol for the integral. Literally, on a specific day, on a specific page, he took a long letter S and used it to denote the sum of infinitely many, infinitely small quantities. On November 11th of the same year, he wrote down the formula d of x to the n equals n times x to the n minus 1 times dx, the power rule of differentiation in differential form. The birth of calculus notation can be dated to the day. This notation, dx, dy, dy over dx, the integral sign, is used around the world to this day. It turned out to be so convenient, so intuitive, so flexible that it displaced every alternative. Newton denoted derivatives by dots above letters, x dot for velocity, x double dot for acceleration. And this dot notation is still found in some branches of physics, particularly mechanics and cosmology. But it is clumsy and does not scale well. What if you need the third derivative, the fourth, the 10th? Newton stacked more dots. Leibniz wrote d squared y over dx squared, d cubed y over dx cubed, d to the ny over dx to the n. The system scales naturally. And what if the function depends on several variables? In Leibniz's notation, partial f over partial x and partial f over partial y, partial derivatives with respect to x and y, are written simply and clearly. Newton's notation has no convenient way to express this. Leibniz thought about notation far more carefully than Newton did. For Newton, symbols were shorthand, a way to jot down a thought quickly. For Leibniz, symbols were tools for thinking. A well-chosen symbol does not merely record an idea, but suggests new ones. Here is a simple example of why Leibniz's notation is so good. The chain rule, the rule for differentiating compositions, in Leibniz's notation is written as dy over dx equals dy over du times du over dx. It looks like ordinary fraction cancellation. The du's in the numerator and denominator cancel. Of course, dy over dx is not a real fraction, and the cancellation is not an algebraic operation, but a mnemonic convenience. But precisely because the notation suggests the right answer, it is so useful. It lets intuition work. Leibniz published his work in 1684, a paper in the journal Acta Eruditorum, one of the first scientific journals in Europe, under the title Nova Methodus pro maximis et minimis, itemque tangentibus, quae nec fractas, nec irrationales quantitates moratur, et singulare pro illis calculi genus. A new method for maxima and minima, as well as tangents, which is not obstructed by fractional or irrational quantities, and a remarkable type of calculus for them. The program was right there in the title, a universal method that works for any expression without restrictions. The paper was, by general admission, monstrously dense and hard to read. Leibniz had packed an enormous number of ideas into a few pages. The Bernoulli brothers admitted they spent weeks trying to understand it, but it was published. It was available.
and the European mathematical community, initially puzzled, gradually adopted the new method.
The key role in spreading it was played by the Bernoulli brothers, Jacob and Johann, from Basel, Switzerland. They became the champions of Leibniz's calculus, extended it, applied it to new problems, and helped turn it from a dense paper into a working tool that could be taught. Johann Bernoulli, in particular, was one of the most influential mathematics teachers of his time. Among his students was the Marquis de l'Hôpital, who in 1696 published the first calculus textbook in history, based on Bernoulli's lectures. L'Hôpital's rule, a method for computing limits of indeterminate forms like 0 over 0, was actually discovered by Johann Bernoulli, but entered history under L'Hôpital's name because he published it. Bernoulli had ceded the right of publication for money, for an annual stipend of 300 livres, and regretted it for the rest of his life. This is one of the earliest cases of the commercialization of a mathematical discovery, and simultaneously one of the most ironic. The formula is forever linked not to the name of its creator, but to the name of the man who paid for the right to print it. Here is how L'Hôpital's rule works for completeness. If when you substitute the value a, both the numerator and denominator of a fraction go to 0, that is, you get the form 0 over 0, then the limit of the fraction equals the limit of the ratio of the derivatives of the numerator and denominator. That is, the limit of f of x over g of x equals the limit of f prime of x over g prime of x. You differentiate the top and bottom separately and try again. If you still get 0 over 0, differentiate once more. A simple, elegant method that resolves an entire class of problems that look hopeless. And so Leibniz's calculus spread across continental Europe, through publications, through students, through textbooks, through active correspondence. Johann Bernoulli corresponded with dozens of mathematicians. Leibniz himself was a prolific letter writer. He left behind more than 15,000 letters. Scientific knowledge traveled through this correspondence network faster than through books. A letter arrived in weeks. A book took months to print. Calculus became the working tool of an entire generation of mathematicians. And then, from England, came a cry. Newton, by that point already the president of the Royal Society, England's chief scientific body, the man called the greatest living Englishman, saw Leibniz's work and was absolutely convinced that Leibniz had stolen his ideas. Newton's position rested on the following. I developed this in 1665 and 66. I wrote it down in notebooks. I showed it to people, Barrow, Collins. In 1676, I sent 2 letters to Leibniz through Henry Oldenburg, the secretary of the Royal Society, in which I hinted at my results, though I encrypted the key statements in anagrams. Leibniz saw those letters. Therefore, Leibniz borrowed my method. Leibniz's position was compelling and documented. I developed this independently, starting around 1673. My diaries contain dated entries showing the gradual development of ideas, from geometric problems through tangents to differentials. Newton's letters through Oldenburg contained anagrams that were impossible to decipher. They could not have been the source of my ideas. Look at my manuscripts. Look at the fact that I came from geometry and tangents, while Newton came from physics and motion. We have different starting points, different notations, different conceptual frameworks. The fact that we arrived at the same result proves not plagiarism, but that we were both pursuing the same deep mathematical truth. By 1712, the conflict had grown so bitter that the Royal Society of London, England's supreme scientific body, convened a formal investigation.
Ostensibly, the committee was to objectively examine the evidence from both sides. Letters, manuscripts, dates were assembled. The committee ruled, priority belongs to Newton. Leibniz was accused, if not outright, then by implication, of borrowing ideas from Newton's letters, which Leibniz had seen through Oldenburg in the 1670s. The ruling was presented as an objective, impartial finding. In reality, the report, the Commercium Epistolicum, was compiled under the direct supervision of Newton himself. He was the president of the Royal Society and used his full institutional power. He personally selected the committee members, personally decided which documents to include in the evidence base, personally wrote the preface to the report, and, in all likelihood, much of the report itself. The investigation was not a trial, but a prosecution dressed up as a trial. The war grew dirtier. Newton, using anonymous reviews and proxy authors, published attacks on Leibniz in the Philosophical Transactions, the journal of the Royal Society, which he himself oversaw. Leibniz responded in continental journals. Supporters of both camps jumped in. Johann Bernoulli, defending Leibniz, lobbed problems that were simpler in Leibniz's notation, demonstrating the superiority of his approach. The English took offense. The conflict spilled beyond mathematics. It became a matter of national honor. English science versus continental, Newton versus Leibniz, island genius versus German polymath. Rational discussion about priority drowned in emotion, pride, and politics. Leibniz died on November 14, 1716, embittered, worn down by gout, largely abandoned by the very patrons who had supported him for decades. George Ludwig, the Elector of Hanover, whom Leibniz had served for over 30 years, had by then become King George I of Great Britain and had forbidden Leibniz from accompanying him to London. Leibniz spent his last years in Hanover working on a history of the Welf dynasty, a project his patrons considered more important than all his philosophical and mathematical works. The dispute with Newton remained unresolved and poisoned his life. The funeral was modest, almost invisible for a city where Leibniz had lived for decades. One observer noted that he was buried more like a robber than a man who had been the ornament of his country, almost without ceremony. Of his patrons and employers, not one attended the funeral. The only person from the royal court who visited the grave was his personal secretary. Today, the consensus among historians is this: both arrived at calculus independently. Newton first chronologically, developing his method in 1665. Leibniz independently, starting around 1673 and publishing first in 1684. The key evidence for independence lies in the deep differences in their approaches. Newton came from physics, motion, velocity, time, fluxions. Leibniz came from geometry and philosophy, differentials, sums, symbols. They developed different notations, Newton's dots versus Leibniz's D and integral sign. They used different conceptual frameworks. If Leibniz had simply copied Newton, his method would look like a copy. But it looks like a completely independent construction, built by a different architect from different materials to a different plan that led to the same building. The fact that their methods turned out to be mathematically equivalent testifies not to plagiarism, but to the depth of the ideas themselves. Ideas that, as we have seen, were independently discovered in the most different corners of the world across the most different eras. And the most ironic footnote to the whole story, Leibniz's notation 1. dx, dy, dy over dx, the integral sign, that is all Leibniz. The whole world learns calculus in the language of Leibniz, not Newton.
But the consequences of the war extended far beyond notation and beyond the lives of two men. They determined the trajectory of entire national mathematical schools for a century. England, out of national pride and loyalty to its greatest hero, refused to adopt Leibniz's approach and clung to Newton's notation. Fluxions, dots above letters, geometric style of reasoning. British mathematicians stubbornly worked within the framework their national genius had established.
They did it out of respect, but respect turned into isolation. Continental Europe, France, Germany, Switzerland, Russia used Leibniz. And because Leibniz's notation was objectively more convenient, more powerful, and more scalable, continental mathematicians advanced faster. The Bernoulli brothers, Euler, Lagrange, Laplace, Fourier, Cauchy, all the great names of the 18th and early 19th centuries belonged to the continent. Britain, which in Newton's era stood at the pinnacle of world mathematics, slipped to the periphery. Only in the early 19th century did a group of young Cambridge mathematicians, Charles Babbage, John Herschel, and George Peacock, found the Analytical Society, whose aim was, in Babbage's witty phrase, to replace the dot age of the university with the D-ism of the continent, a pun. Dotage meaning senile decay from Newton's dots, D-ism from Leibniz's D. They translated continental textbooks into English and pushed Leibniz's notation into the Cambridge curriculum. British mathematics began to recover, but it had lost a century. Leibniz lost the war for recognition in his lifetime, but won the war for the future of mathematics. Every time you write dy over dx or an integral sign, you are using his language. And now, it is time at last to explain what this inverse relationship between differentiation and integration actually is. The one Barrow saw, Newton used, and Leibniz formalized. The fundamental theorem of calculus, the discovery for which, in a sense, all the predecessors had been working, from Archimedes to Fermat. The discovery that turned calculus from a collection of separate tricks into a single, working system. We already know what the derivative is. It answers the question, how fast? How fast a function is changing at a given point. The derivative turns a position function into a velocity function into an acceleration function, a cost function into a marginal cost function. Now let us talk about the second fundamental operation, integration. If differentiation is the taking apart, the disassembly, the extraction of instantaneous change, then integration is the putting together, the adding up, the computation of total accumulation. Here is the simplest situation. You are driving a car at 60 miles per hour for exactly 2 hours. How far did you go? 120 miles. Distance is speed times time. Easy. Graphically, if you draw a speed graph, a horizontal line at 60 miles per hour, and shade the rectangle from 0 to 2 hours, its area is exactly 120. The area under a speed graph is distance. Remember this connection. It is fundamental. But what if the speed was changing? What if you started from a standstill, gradually accelerated to 60 miles per hour, then braked before a turn, sped up again, then sat at a red light? The speed graph is not a horizontal line, but a curve that rises, falls, and drops to 0. The area under that curve is the total distance. But how do you compute the area under a curve when it is not a rectangle, not a triangle, not any other simple shape? You cannot just multiply. There is no single number, speed, that you can plug into a formula. And here is what you do. You break the time into small pieces. During each small piece, the speed did not change much. You can treat it as roughly constant. Multiply that roughly constant speed by the length of the piece, and you get the approximate distance covered in that piece. Add up the distances for all the pieces. You get an approximate total distance. The smaller the pieces, the more accurate the approximation. In the limit, infinitely many pieces, each
infinitely thin. The approximation becomes the exact answer. This is the integral. The word integral comes from the Latin integer, meaning whole, complete. Integration is the process of assembling the whole from infinitely many, infinitely small parts. Differentiation took things apart. It gave instantaneous speed, local slope, behavior at a single point. Integration puts them back together. It gives total distance, total area, the cumulative result. Let us look at this geometrically, because the geometric picture is one of the most intuitive in all of calculus. Draw the graph of a function, any curve. Pick two values on the x-axis, a and b. Shade the region between the curve and the x-axis from a to b. The area of that shaded region is the definite integral of the function from a to b. How do you compute that area? With the same technique our predecessors used, from the Babylonians to Archimedes, from Cavalieri to Fermat.
Break the region into thin vertical strips, as if you were slicing a piece of pie into very narrow slivers. Each strip is almost a rectangle. It would be a perfect rectangle if the top edge were straight rather than curved. But if the strip is narrow enough, the curve barely bends inside it, and the rectangle is a good approximation. The width of each rectangle is a small increment, delta x. The height is the value of the function at that point, f of x. The area of one strip is f of x times delta x. Add up all the strips. You get an approximation of the area. The narrower the strips, the more of them there are, the more accurate the approximation. With 10 strips, the error is noticeable. With 100, it is small. With 1,000, it is tiny. In the limit, infinitely many, infinitely thin strips, the error vanishes, and you get the exact area.
This limit of sums, formalized by Bernhard Riemann in the 19th century, is called a Riemann sum, and in the limit, it gives the definite integral. The notation, the integral from a to b of f of x dx, reads, the integral from a to b of f of x with respect to dx. The integral sign is the elongated s from summa, a reminder that the integral is a sum. dx is the infinitely small width of a strip. F of x is the height. F of x times dx is the area of one infinitely thin strip. The integral is the sum of all such strips from a to b. Let us look at a concrete example. Find the area under the parabola y equals x squared from x equals 0 to x equals 3. We could try to compute this through Riemann sums, adding up infinitely many rectangles. That would be tedious and technically challenging, but we will not do that because there is a better way. And that way became possible thanks to a discovery that turned all of mathematics upside down. That discovery is the fundamental theorem of calculus. Here is what it says. Suppose you want to compute a definite integral, the area under the graph of a function f from a to b. Instead of adding up infinitely many rectangles, you can do the following. Find a function f whose derivative equals f, that is, f prime of x equals f of x. Such a function is called an antiderivative. And then, simply compute f of b minus f of a. The difference of the antiderivative's values at the endpoints of the interval is the area. The integral from a to b of f of x dx equals f of b minus f of a, where f is any antiderivative of f. Back to our example. The area under y equals x squared from 0 to 3. We need an antiderivative of x squared, a function whose derivative is x squared. We know the power rule. The derivative of x to the n is n times x to the n minus 1. Working backward.
If the derivative needs to be x squared, we need a function whose power is 1 higher, x cubed, with a coefficient that, when differentiated, gives 1. The derivative of x cubed is 3x squared. To get just x squared, divide by 3. So the antiderivative of x squared is x cubed over 3. Check. The derivative of x cubed over 3 equals 3x squared over 3 equals x squared. Correct. Substitute. F of 3 minus f of 0 equals 3 cubed over 3 minus 0 cubed over 3 equals 27 over 3 minus 0 equals 9. The area under the parabola y equals x squared from 0 to 3 is exactly 9 square units. It is worth emphasizing that we got an exact answer, not an approximation, not good enough for engineering purposes, exactly 9. The infinite process of summing infinitely thin strips collapsed into a single arithmetic step. But let us think about how staggering this result is. Integration, finding area, and differentiation, finding slope, at first glance have nothing in common. One is about sums, accumulation, how much in total. The other is about instantaneous change, slope, how fast right now. Two completely different problems. Two completely different questions. Two completely different geometric images. Area is a two-dimensional quantity, a shaded region. Slope is a one-dimensional number, the angle of a tangent. And suddenly it turns out they are inverse operations, like addition and subtraction, like multiplication and division, like encryption and decryption. Differentiation takes apart, integration puts back together. If you differentiate a function and then integrate the result, you get the original function back, up to a constant, because differentiation loses information about the starting point, the vertical shift of the graph. And vice versa. If you integrate a function and then differentiate the result, you also return to the start. It is as if you discovered that a recipe for baking a cake and a list of ingredients are inverse operations. Knowing the recipe, you can recover the ingredient list, and knowing the ingredients, you can recover the recipe. On the face of it, absurd. But in mathematics it works, and it works exactly. This is why the fundamental theorem is not merely a useful computational trick. It exposes a deep structural connection between two fundamental ways of thinking about functions. Rate of change and total accumulation, two sides of the same coin. Inhale and exhale of a single process. It can be put another way. The fundamental theorem says, if you know the rate of a process at every moment, you can reconstruct the entire process. And conversely, if you know the entire process, the function, you can compute its instantaneous rate. Information is not lost in the passage from function to derivative and back, up to the initial condition, the constant of integration. In a sense, this is a statement about wholes and parts. If you know all the parts, instantaneous rates, you can assemble the whole, total distance. If you know the whole, you can take it apart into parts. The whole is determined by the parts. The parts are determined by the whole. Analysis and synthesis, two directions on one road. Barrow saw this in geometric form. Newton used it as a working tool. Leibniz formalized and published it. And from that moment on, calculus ceased to be a collection of clever tricks and became a single, working system. Let us work through a few more examples to feel how this connection operates in practice. The derivative of a constant is 0. A constant does not change. Its rate of change is 0.
The derivative of the number 5 is 0. The derivative of pi is 0.
The inverse operation.
The integral of 0 is a constant. If the rate of change is 0, nothing accumulates, except what was there to start with, hence the plus c, the arbitrary constant of integration. The derivative of a linear function, y equals mx plus b, is m, its slope. A straight line has a constant slope. The inverse. The integral of a constant m is mx plus c, a linear function. If you accumulate something at a constant rate, the result grows linearly. The derivative of e to the x is e to the x. The function e to the x is the only function, up to scaling, that is its own derivative. Its rate of growth at every point equals its current value. Think about what that means. The bigger the function gets, the faster it grows. The faster it grows, the bigger it gets. Positive feedback, and the result is exponential explosion.
The number e, the base of the natural logarithm, approximately 2.71828, is one of the fundamental constants of mathematics, alongside pi. It shows up everywhere there is continuous growth, in bank interest, in radioactive decay, in population dynamics, in thermodynamics, in probability theory. As pi is tied to the circle, E is tied to growth. If you have money in a bank account earning continuously compounded interest added not once a year, not once a month, but continuously, infinitely often over infinitely small intervals, and the annual rate is 100%, then after 1 year, your balance will have grown by exactly a factor of E. That is why exponential functions describe population growth. Each bacterium divides, and the number dividing is proportional to the current total. Radioactive decay. Each atom has the same probability of decaying per unit time, and the rate of decay is proportional to the number of remaining atoms. The spread of epidemics in the early stage. Each infected person contacts a certain number of people, and the rate of spread is proportional to the number infected. And compound interest. Carbon dating, the method for determining the age of archaeological finds, is based on the exponential decay of radioactive carbon-14. The half-life of carbon-14 is about 5,730 years. Knowing the fraction of remaining carbon-14, you solve an exponential equation and get the age. This method is used in archaeology, paleontology, and climatology, and at its core lies the differential equation dy over dt equals minus ky, whose solution is an exponential. The derivative of sine of x is cosine of x. The derivative of cosine of x is minus sine of x. Sine and cosine are waves, shifted relative to each other by a quarter of a period. The derivative of a wave is another wave, shifted by another quarter. If you keep differentiating, you get a cycle. The derivative of sine is cosine. The derivative of cosine is minus sine. The derivative of minus sine is minus cosine. The derivative of minus cosine is sine. 4 differentiations and you are back where you started. Differentiation rotates the sine wave by a quarter turn each time. This is connected to Euler's formula. Remember, e to the I theta equals cosine theta plus I times sine theta. Multiplying by I is a quarter turn rotation in the complex plane. Differentiation is also a quarter turn. 2 seemingly unrelated facts turn out to be the same thing. Physical intuition helps. Imagine a pendulum. It swings in a sinusoidal pattern. Displacement from equilibrium is sine of t. The pendulum's velocity, the derivative of displacement, is cosine of t. Velocity is greatest at the middle of the swing, where displacement is 0. and 0 at the extreme points, where the pendulum momentarily pauses before swinging back. Acceleration, the second derivative, equals minus sine of t, directed opposite to the displacement. The farther the pendulum is from equilibrium, the harder it is pulled back. This is the definition of a harmonic oscillator, and from it follows that y double prime plus y equals 0, one of the simplest and most important differential equations. The derivative of the natural logarithm, natural log of x, is 1 over x. The logarithm grows, but ever more slowly as x increases, and 1 over x captures exactly that deceleration. The bigger x gets, the smaller 1 over x becomes, and the more slowly the logarithm grows. Natural log of 10 is about 2.3, natural log of 100 about 4.6, natural log of 1,000 about 6.9. Each tenfold increase in x adds only about 2.3 to the value of the logarithm. Logarithmic growth is the antipode of exponential. If the exponential describes acceleration without limit, the logarithm describes deceleration without stopping. Interestingly, the integral of 1 over x is natural log of x plus c. The function 1 over x is the only power x to the n for which the power rule of integration, the integral of x to the n dx equals x to the n plus 1 over n plus 1, does not directly work. At n equals minus 1, the denominator n plus 1 is 0. The natural logarithm fills this gap. It is the antiderivative of 1 over x, and its existence is one of the reasons logarithms are so important in calculus. Each of these formulas is the result of applying the limit definition of the derivative. Each can be derived from scratch by substituting the function into the expression f of x plus h minus f of x, all over h, and sending h to 0. But in daily practice, mathematicians and engineers use ready-made rules, the power rule, the product rule, the chain rule, just as you use the multiplication table instead of adding numbers one by one. Let us look at a physical application that ties everything together and shows how differentiation and integration work in tandem. You drop a ball from the roof of a building about 328 feet tall. We ignore air resistance. The ball falls freely under gravity alone. The ball's height above the ground at time t is described by the function h of t equals 328 minus 16t squared. The number 16 is half the acceleration due to gravity in feet per second squared. G is approximately 32 feet per second squared. Where did this formula come from? From integration. Acceleration is constant. A equals minus 32 feet per second squared. Negative because it points downward. Integrate the acceleration. You get velocity. V of t equals minus 32t plus v naught. Initial velocity v naught equals 0. The ball was dropped, not thrown. Integrate the velocity. You get position. H of t equals minus 16t squared plus h naught. Initial height, h naught, equals 328 feet. Result, h of t equals 328 minus 16t squared. When does the ball hit the ground? Set h of t equal to 0. 328 minus 16t squared equals 0. T squared is approximately 20.5. T is approximately 4.5 seconds. What is the ball's speed as a function of time? Take the derivative of height. V of t equals h prime of t equals minus 32t. The minus sign means the ball is moving downward. At the moment of impact, at t approximately 4.5, v is approximately minus 32 times 4.5.
which is approximately minus 144 feet per second. That is roughly 98 miles per hour. What is the acceleration? Take the derivative of velocity. A of t equals v prime of t equals minus 32 feet per second squared, a constant. The acceleration of gravity is constant. This is Newton's insight that gravity pulls all objects downward with the same acceleration, regardless of their mass. How far did the ball fall? That is the integral of the absolute value of velocity over time, or, more simply, 328 feet, because it fell from a height of 328 feet. All of this from a single position function and the basic operations of calculus. Position, differentiate. Velocity, differentiate. Acceleration. Acceleration, integrate. Velocity, integrate. Position.
Differentiation and integration. Moving up and down the same staircase. Each step is a different physical quantity, but they are all connected through the same operations. This is perhaps the deepest connection between calculus and physics. The laws of nature are formulated as statements about derivatives, forces, accelerations, fluxes, while the quantities we observe, positions, distances, accumulated amounts, are obtained by integration. Physics lives in derivatives. We observe integrals. Let us feel once more what just happened. A computation that directly, through Riemann sums, would require summing an infinite series, reduces to a single substitution. It is as if you had a long, exhausting way to walk somewhere and suddenly discovered a tunnel that leads straight there. The tunnel is the fundamental theorem. It converts a summation problem into an antiderivative problem, and the second problem is usually far easier. Try another example. The area under the curve y equals x cubed from 0 to 2. The antiderivative of x cubed is x to the fourth over 4. Check. The derivative of x to the fourth over 4 equals 4x cubed over 4 equals x cubed. Correct. Substitute. 2 to the fourth over 4 minus 0 equals 16 over 4 equals 4. The area is 4. 30 seconds. And now, the area under the sine wave y equals sine of x from 0 to pi. The antiderivative of sine of x is minus cosine of x, because the derivative of minus cosine of x is sine of x. Substitute. Minus cosine of pi minus the quantity minus cosine of 0 equals minus -1 minus -1 equals 1 plus 1 equals 2. The area under one arch of the sine wave is exactly 2. There is something deeply satisfying about such a round shape having such a simple area. Here is one more example showing the geometric power of integration. Suppose you want to find the area of a circle with radius r. You can slice the circle into thin concentric rings, like the layers of an onion. Each ring at distance x from the center has a circumference of 2 pi x and a thickness of dx. The area of each thin ring is approximately 2 pi x times dx. Summing all the rings from x equals 0 to x equals r, that is, integrating 2 pi x from 0 to r, the antiderivative of 2 pi x is pi x squared. Substitute. Pi times r squared minus pi times 0 squared equals pi r squared. The area of a circle is pi r squared. You knew that formula, of course, but now you see where it comes from slicing the circle into infinitely thin rings and adding their areas. This is the general strategy. Slice into thin pieces, integrate, add up. It works for areas, volumes, arc lengths, centers of mass, moments of inertia, for virtually any quantity you want to compute for a continuous object.
And integration also lets you compute work. Imagine a spring.
When you stretch a spring, it resists with a force proportional to the stretch. This is Hooke's law. If you have stretched the spring a distance x from its natural length, the restoring force is k times x, where k is the spring constant. How much work do you need to stretch the spring from 0 to, say, about 3 feet and 3 inches? Work is force times distance, but the force changes as you stretch. At the start, the spring barely resists, and by the end, the resistance is at its maximum. You cannot just multiply, you need to integrate. W equals the integral from 0 to 1 of kx dx, which equals k times x squared over 2, evaluated from 0 to 1, which equals k over 2. The work equals k over 2. Without integration, this problem is impossible, because there is no single force value you can plug into the formula work equals force times distance. The force changes continuously, and the only way to cope is to break the distance into infinitely small pieces. Multiply each by the corresponding force and add. Let us look at one more example, the volume of a solid of revolution. Take the parabola y equals the square root of x from 0 to 4 and rotate it around the x-axis. You get a paraboloid, a shape resembling a satellite dish. How do you find the volume? Slice the solid into thin discs perpendicular to the x-axis. Each disc, at distance x from the origin, has a radius y equals the square root of x and a thickness dx. The volume of a disc is pi times y squared times dx, which is pi times x times dx. Sum all the discs from 0 to 4. The integral from 0 to 4 of pi x dx equals pi times x squared over 2, evaluated from 0 to 4, which equals pi times 16 over 2, which is 8 pi, approximately 25.13 cubic units. The same method, slice into thin pieces and add, works for any solid of revolution, any shape, any mass distribution. Center of mass, integral. Moment of inertia, integral. Arc length, integral. Surface area, integral. One and the same strategy. Slice the continuous into infinitely thin pieces. Compute each one's contribution. Integrate. We are now at the very center of our story, the point where all threads converge. The Egyptians integrated without knowing it. The Babylonians integrated without suspecting. Archimedes approached the limit. Madhava developed infinite series. Fermat differentiated. Barrow saw the connection. Newton and Leibniz assembled it all into a system. And after them, the system began to grow at staggering speed. Because the next question arose, what can this machine do? How far can it reach? What problems does it solve? The answer? Virtually every problem that involves continuous change. And in nature, continuous change is everywhere. Here it is worth pausing and taking stock of where we are in our story. We have crossed 4,000 years, from clay tablets to formulas that can be applied to any smooth curve. We have seen how an idea born in practical problems, the volume of a stone block, the trajectory of a planet, became a universal method. We have seen the two fundamental operations, differentiation and integration, and the stunning connection between them. We hold a working tool in our hands, a
And now, the people who took that tool and raced with it so far that they surprised even themselves at where it led. And along the way, they discovered that the tool rested on a foundation that was cracking. After Newton and Leibniz, calculus exploded. The 18th century was the era when calculus, now equipped with language and method, attacked problems with a hunger that had been building for centuries.
Problems about curves, motion, oscillations, optimal shapes, fluid flow. One after another, they yielded to the new tool. And the first to rev up the machine were the Bernoulli brothers, Jakob and Johann, from Basel, Switzerland. The Bernoulli family is one of the most distinguished mathematical dynasties in history. Across 3 generations, it produced 8 major mathematicians. Jakob and Johann were, in effect, the first generation to take Leibniz's calculus and seriously push it forward. Between themselves, the brothers were locked in fierce rivalry. Who could solve the harder problem? Who could publish first? Who was smarter? Jakob, the elder, once publicly humiliated the younger Johann by pointing out an error in his solution to a problem about isoperimetric curves, curves of a given length that enclose the maximum area. Johann responded with a barrage of caustic publications, accusing Jakob of stealing his methods. Johann later threw his own son Daniel, future great mathematician, author of Hydrodynamica, out of the house for winning a prize from the Paris Academy of Sciences that Johann himself had been competing for. Father and son shared the prize, and Johann could not bear it. He even published a book in which he tried to show that Daniel's results had actually been obtained by Johann himself earlier. The Bernoulli family dynamics are a drama unto themselves, full of envy, grievances, and intellectual rivalry that, for all its ugliness, drove mathematics forward. But for all their human failings, the Bernoulli family's mathematical achievements are towering. They worked with curves, with optimization problems, with what we now call the calculus of variations. The science of finding not a number that optimizes a function, but an entire function that optimizes some quantity. One of the most beautiful problems they solved is the brachistochrone problem. It asks, along what curve will a ball roll from one point to another, located lower but not directly below the first, in the shortest time under gravity? Intuitively, it seems the answer should be a straight line, the shortest distance between 2 points. But the straight line is not optimal. Here is why. If the curve is steeper at the start, the ball picks up speed faster thanks to gravity, and although it covers a longer distance, it covers it much more quickly because it is moving at higher speed for most of the trip. The answer is a cycloid, the curve traced by a point on the rim of a rolling wheel. If you tape a marker to the edge of a bicycle wheel and roll the wheel along a wall, the marker draws a cycloid, a series of identical arches. It is along precisely such an arch that a ball rolls from one point to another in the shortest time. Johann Bernoulli found this solution and published the problem as a challenge in the journal Acta Eruditorum in June of 1696, giving 6 months to solve it. When few answers arrived by the deadline, he extended it by another year. Newton, according to legend, received the problem on the evening of January 29, 1697, after a hard day at his post as Warden of the Royal Mint, and solved it by 4 in the morning. He submitted the solution anonymously. Bernoulli, upon seeing it, reportedly said, "Tanquam ex ungue leonem." I recognize the lion by his claw. The brachistochrone problem matters as more than a beautiful puzzle. It became the starting point for an entire branch of mathematics, the calculus of variations, which deals not with optimizing numbers, but with optimizing functions. Finding not a point of maximum or minimum, but an entire curve that optimizes some quantity. Out of the calculus of variations grew Lagrangian mechanics, principle of least action, which Feynman called the most fundamental principle in physics, control theory, and much more. But the towering figure after Newton and Leibniz is Leonhard Euler. If Newton and Leibniz built the engine, Euler is the man who put that engine on wheels, wings, and propellers all at once. Euler was born in 1707 in Basel, Switzerland, and studied under Johann Bernoulli. He was effectively Bernoulli's best student. He is one of the most prolific mathematicians in history. Over his lifetime, he published roughly 800 papers and books, and several hundred more were published posthumously. The St. Petersburg Academy of Sciences, where Euler spent most of his career, continued publishing his unpublished manuscripts for nearly 50 years after his death. Euler lost the sight in his right eye at about 31 after a severe illness in 1738 and went completely blind by 60. The loss of vision did not slow his work. He kept dictating mathematical papers at such speed that his secretaries could barely keep up. Half of his output was produced after he went fully blind. Laplace, another great mathematician, said, "Read Euler, read Euler. He is the master of us all." Euler worked in virtually every area of calculus and mathematics in general, as well as in physics, astronomy, mechanics, optics, shipbuilding, and music theory. Euler introduced most of the notation we use today, the symbol sigma for summation, the notation f of x to denote a function. Before Euler, functions were described in words or informal notation. It was Euler who standardized the f of x form we have used ever since. The letter e for the base of the natural logarithm. Euler proved this number is irrational. The letter I for the imaginary unit, the square root of -1. The letter pi for the ratio of circumference to diameter. Although the symbol pi had been used before Euler, it was his authority that established it as the standard. When you write a formula using these symbols, you are writing in a language largely invented by Euler. One example of Euler's computational virtuosity is his solution of the Basel problem. The problem, posed by Pietro Mengoli in 1650, asked, what is the sum of 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on? That is, the sum of the reciprocals of the squares of the natural numbers. The sum is finite, unlike the harmonic series, but what it actually equals, nobody could find. The problem stood open for 80 years. Euler solved it in 1735. The sum equals pi squared over 6. The appearance of pi in the answer is completely unexpected, since the problem contains neither circles nor trigonometry. This discovery brought Euler instant fame in the mathematical world. Euler advanced the calculus of variations, the branch of calculus that seeks not a value optimizing a function, but an entire function optimizing some quantity. The difference. Ordinary optimization asks, at what x is f of x minimal? The calculus of variations asks, what function y of x minimizes the integral of f of x, y, y prime, dx? The answer is not a number, but an entire curve. It is the calculus of variations that underlies Lagrangian mechanics, a formulation of classical physics that, in many respects, is deeper and more powerful than Newton's. The principle of least action, one of the most fundamental principles in physics, states that a physical system evolves from one state to another along the path on which a certain quantity, the action, is minimized. Finding that path is a problem in the calculus of variations. Euler also worked with differential equations and connected calculus to complex numbers and to number theory. Euler's formula deserves special mention because many mathematicians consider it the most beautiful equation in all of mathematical history. Its beauty lies in uniting 5 seemingly unrelated constants and operations. formula states e to the I theta equals cosine of theta plus I times sine of theta, where I is the imaginary unit, the number whose square equals -1, and theta is a real number representing an angle in radians. If you plug in theta equals pi, you get e to the I pi plus 1 equals 0. A single equation linking the 5 most important constants in mathematics. E, the base of the natural logarithm, the number that describes continuous growth. I, the imaginary unit, the gateway to complex numbers. Pi, the ratio of circumference to diameter, the fundamental constant of geometry. 1, the multiplicative identity, the starting point of counting. And 0, the additive identity, absence, emptiness. 3 fundamental operations: addition, +1, multiplication, I times pi, and exponentiation, e to the power of. All in a single line, 7 symbols. The physicist Richard Feynman, seeing this formula for the first time as a teenager, wrote in his diary, "The most remarkable formula in mathematics." The mathematician Keith Devlin called it Euler's jewel. It appears on t-shirts, tattoos, and memes, a rare case of a mathematical equation becoming a cultural icon. Where does this formula come from? From the Taylor series for the exponential, applied to a complex argument. Write out the Taylor series for e to the x. Plug in x equals I theta, and separate the resulting terms into real and imaginary parts. The real part turns out to be the Taylor series for cosine of theta. The imaginary part, the series for sine of theta. The exponential, sine, and cosine, which in the real world seem like entirely different functions, turn out in the complex world to be manifestations of a single entity. Geometrically, Euler's formula says the following: e to the I theta is a point on the unit circle in the complex plane, located at angle theta from the positive real axis. Multiplying by e to the I theta is a rotation by the angle theta. The exponential is rotation. The connection between exponential growth and rotation, between straight line motion and circular motion, one of the deepest discoveries in mathematics, and it would have been impossible without calculus, without Taylor series, without infinite sums. The Taylor series, though its special cases were known to Madhava centuries before Taylor, is perhaps the most practically important achievement of this era. The idea, any well-behaved function can be represented as an infinite polynomial, an infinite sum of power terms with specific coefficients. And those coefficients are determined by the values of the function and all its derivatives at a single point. For example, e to the x equals 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, and so on, where n factorial is the product of all integers from 1 to n. Sine of x equals x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, and so on. Cosine of x equals 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, and so on. Let us see how this works with numbers. Compute e to the 1, the number e itself, using the Taylor series. E to the 1 equals 1 plus 1 plus 1/2 plus 1/6 plus 1 over 24 plus 1 over 120, and so on. Take the first 7 terms. 1 plus 1 plus 0.5 plus 0.1667 plus 0.0417 plus 0.0083
plus 0.0014 equals 2.7181. The true value of E is approximately 2.71828. After just 7 terms, the accuracy is 4 decimal places. Each subsequent term adds another 1 or 2 digits of precision because the factorials in the denominators grow very fast. Or compute sine of 0.5, the sine of half a radian, about 29 degrees. Sine of 0.5 is approximately 0.5 minus 0.5 cubed over 6 plus 0.5 to the 5th over 120, which equals 0.5 minus 0.0208 plus 0.00026, which equals 0.4795. The exact value is 0.47943. 3 terms of the series, and accuracy to 4 decimal places. This is exactly how calculators and computers evaluate sines, cosines, exponentials, and logarithms. Inside the processor, there is no sine table. There is an algorithm that takes a few terms of the Taylor series, or a modified series optimized for speed, and gets the answer to the required precision.
Taylor series, discovered by Madhava in the 14th century and formalized by Taylor in the 18th, run inside every calculator, every smartphone, every computer on the planet. But in all this beauty and power, something troubling was hidden. A problem that for a century and a half nobody could, or wanted to, solve. A problem that grew like a crack in the foundation of a building that kept rising higher, and that more and more depended on it. All of calculus, all of Newton's methods, all of Leibniz's notation, all of Euler's series, all of the Bernoulli's formulas, rested on the notion of infinitesimally small quantities. Quantities that are infinitely small but not equal to 0. Quantities that you use as non-zero, so you can divide by them, and then discard as 0, so you can simplify the formula. And nobody could coherently explain what these quantities are. They are not 0 because you cannot divide by 0. They are not positive numbers because they are less than any positive number. What are they? 18th century mathematicians dealt with this question the way you deal with a pothole in the road. Carefully, trying not to look down. D'Alembert was honest about it. Go forward and faith will come to you. Euler worked with infinitesimals with the virtuosity of a circus acrobat, never once falling, but unable to explain why he did not fall. In 1734, an Irish bishop named George Berkeley wrote a pamphlet that struck at the very heart of calculus. The pamphlet was titled The Analyst, and in it, Berkeley dissected the logical inconsistency on which the entire method rested with surgical precision. When you take a derivative, you divide by h and then set h equal to 0. But if h equals 0, you divide it by 0, which is impermissible. And if h is not 0, you have no right to then say it is. You are using 2 mutually exclusive assumptions simultaneously. H is not 0, so you can divide, and h is 0, so you can drop the remaining terms. Berkeley sarcastically observed, "And what are these fluxions? The velocities of evanescent increments. And what are these same evanescent increments? They are neither finite quantities, nor quantities infinitely small, nor yet nothing. May we not call them the ghosts of departed quantities? The image stuck in history because it hits the mark perfectly. Infinitesimals are ghosts, present when needed, gone when inconvenient." And Berkeley was right. The way Newton and Leibniz used infinitesimals was logically inconsistent by the standards of their own time. They got correct answers. Bridges stood, planets flew along computed orbits. But the reasoning leading to those answers was not watertight. Mathematics that worked brilliantly while standing on a logically shaky foundation.
a building rising skyward while the foundation cracked. It would take more than another century to patch that crack. But while it remained unpatched, the machine kept running, and running brilliantly. Calculus by this point is a working machine. We have the derivative, how fast, the integral, how much in total, the fundamental theorem, they are inverses of each other, and a set of rules, power, product, chain. But there are a few more techniques worth seeing. They convey the power and elegance of the whole system and show why calculus turned out to be such a universal tool. Let us start with optimization, one of the most practical applications of the derivative. The idea is simple and beautiful. If you want to find the value of the argument at which a function reaches its maximum or minimum, you need to find the points where the derivative equals 0. Why? Recall the geometric meaning of the derivative. It is the slope of the tangent to the graph. At a maximum, the curve levels off. It transitions from rising to falling. At that transitional moment, the tangent is horizontal and its slope, the derivative, is 0. The same at a minimum. The curve transitions from falling to rising. The tangent is horizontal. The derivative is 0. This gives a simple algorithm. 1. Take the derivative of the function. 2. Set it equal to 0. 3. Solve the equation. The solutions are candidates for maxima and minima. 4. Check the second derivative to distinguish a maximum from a minimum. Here is a classic problem. A farmer has about 200 feet of fencing. He wants to enclose a rectangular plot along a river, so he needs fencing on only 3 sides. The 4th side is bounded by the river. What dimensions give the maximum area? Let x be the length of each of the 2 sides perpendicular to the river. Then the side parallel to the river is 200 minus 2x, all the remaining fence. The area, A equals x times the quantity 200 minus 2x, which equals 200x minus 2x squared. Take the derivative. A prime of x equals 200 minus 4x. Set it equal to 0. 200 minus 4x equals 0. X equals 50. With perpendicular sides of 50 feet each and a parallel side of 100 feet, the area is maximized. 50 times 100 equals 5,000 square feet. To confirm this is a maximum and not a minimum, take the second derivative. A double prime of x equals minus 4. It is negative, meaning the curve is humped at this point, concave down, and we have indeed found a maximum. Here is another classic optimization problem. You want to manufacture a cylindrical can of a given volume V using the least amount of metal. The surface area of a cylinder, S equals 2 pi r squared plus 2 pi r h, 2 circular ends plus the lateral surface. Volume, V equals pi r squared h, so h equals V over pi r squared. Substitute. S equals 2 pi r squared plus 2v over r. Take the derivative with respect to r. ds over dr equals 4 pi r minus 2v over r squared. Set it equal to 0. 4 pi r equals 2v over r squared. So r cubed equals v over 2 pi. And at this r, the height h equals 2r. A can whose height equals its diameter. This is why most real cans have roughly these proportions. Engineers solved the same problem, and calculus gave them the answer. Optimization is one of the most directly useful applications of the derivative. Any problem of the form, find the best option, maximum profit, minimum cost, shortest path, least material, is solved by setting the derivative equal to 0. In economics, marginal cost is the derivative of total cost with respect to the volume of production. Marginal revenue is the derivative of total revenue. Maximum profit occurs when marginal revenue equals marginal cost, that is, when the derivative of profit equals 0. Economists use calculus daily.
though many may not think of it as calculus. For them, it is simply marginal analysis, a standard tool. The second derivative is the derivative of the derivative. If the first derivative says how fast the function is changing, the second says how fast the rate of change is changing. Physically, if the function is position, the first derivative is velocity, the second is acceleration. When you stand in an elevator and feel your stomach drop as it starts to rise, you are feeling the second derivative of your position. You do not feel velocity. In an airplane cruising at constant speed, you feel motionless. But you do feel acceleration, the change in velocity. Newton's second law, F equals m times a, is a statement about the second derivative of position with respect to time. Geometrically, a positive second derivative means the curve is cupped upward, like a bowl, like a satellite dish. The tangent lies below the curve. A negative second derivative means it is cupped downward, like a hill, like an upside-down bowl. The tangent lies above the curve. A point where the second derivative changes sign is called an inflection point. The curve switches from bowl to hill, or vice versa. On the graph, it looks like the letter S, with the inflection point at the middle of the S shape. Now, integration techniques. We have already seen that for simple functions, powers, exponentials, trig functions, antiderivatives can be looked up in a table. But real problems often involve more complex expressions, and for those, you need special tricks. Substitution. The method of U substitution works as the reverse chain rule. If the integrand contains a composite function, you can replace the inner part with a new variable and simplify. The idea: if inside the integral you spot a function and its derivative standing side by side, you can fold them into a single variable. For example, the integral of 2x times cosine of x squared with respect to dx. Notice that x squared is the inner function and 2x is its derivative. Substitute. U equals x squared, then du equals 2x times dx. The integral becomes the integral of cosine of u du, which is sine of u, plus c, which is sine of x squared plus c. Integration by parts, the reverse product rule. The name sounds intimidating, but the idea is simple. If you have an integral of a product of two functions, and one of them gets simpler when differentiated, for example, x becomes 1 when differentiated, simpler, while the other is no worse when integrated, for example, e to the x stays e to the x when integrated, no worse. Then the formula, the integral of u dv equals u times v minus the integral of v du, lets you reduce the problem to an easier integral. The formula looks like a magic trick, but behind it stands the product rule read backward. d of uv equals u dv plus v du, so u dv equals d of uv minus v du. And integrating both sides gives the integral of u dv equals uv minus the integral of v du. For example, the integral of x times e to the x dx. Let u equal x. Differentiating it simplifies it to 1. dv equals e to the x dx. Integrating it gives e to the x, no worse. Then du equals dx. v equals e to the x. Substitute. X times e to the x minus the integral of e to the x dx equals x times e to the x minus e to the x plus c, which equals e to the x times the quantity x minus 1 plus c.
Check. The derivative of e to the x times x minus 1 equals e to the x times x minus 1 plus e to the x times 1, which equals x times e to the x. Correct. The remarkable property of the integration by parts formula is that it converts a hard integral into an easy one. In our example, the integral of x times e to the x, hard because it has the product of x and e to the x, turned into the integral of e to the x, easy, taken directly. The art of the method lies in choosing u and d, v, so that the new integral is simpler than the original. There are also trigonometric substitutions, partial fractions, splitting a complex rational expression into a sum of simple fractions, each easily integrated. The DI method, a tabular shortcut for repeated integration by parts, and other techniques. Each is a tool for a particular type of problem, and the art of integration lies in recognizing which tool is needed in each case. And here it is worth being honest. Mastering integration techniques is partly an art. Unlike differentiation, where there is a mechanical algorithm, chain rule plus a table of derivatives, plug in and compute, integration often requires you to see the right substitution or trick. Sometimes you need to guess the form of the answer and check whether it works. Sometimes you try one substitution, find it does not simplify things, and try another. There are entire classes of integrals that cannot be expressed in terms of elementary functions, meaning you will never find a formula for the answer, and the only way out is numerical approximation. This is one reason calculus has a reputation for being hard. Not because the ideas are difficult. The ideas of limits, derivatives, and integrals are intuitively transparent, as we have seen. But because the technical mastery, the ability to quickly spot the right substitution, see the structure of an expression, pick the right tool, requires practice. A lot of practice. Like music. Understanding what a chord is takes 5 minutes. Playing chords fluently takes years of training. But the ideas are beautiful. And in a sense, technique is a matter of training, while ideas are a matter of understanding. Once you understand, you never unlearn. Differential equations, another extension of calculus that deserves mention. A differential equation is an equation in which the unknown is a function, and the equation involves its derivatives. The simplest example, dy over dt equals k times y. The rate of change of y is proportional to y itself. The solution, y equals y naught times e to the kt, where y naught is the initial value. This is exponential growth when k is positive, or exponential decay when k is negative. This single equation describes bacterial population growth, radioactive decay, compound interest, Newton's law of cooling, early stage epidemic spread, and drug absorption in the body. One and the same differential equation, dozens of completely different physical situations. Calculus reveals the common structure hidden behind the outward diversity. A biologist, a banker, a nuclear physicist, and a pharmacist are all solving the same problem, just plugging in different numbers for k and y naught. More complex differential equations describe oscillations. The equation y double prime plus omega squared times y equals 0 describes simple harmonic motion. A pendulum, a spring, the oscillation of electric current in a circuit. Its solution is y equals a times cosine of omega t plus phi, a sinusoidal wave. Add friction, a term proportional to velocity, and you get damped oscillation. Y equals a times e to the minus gamma t times cosine of omega t plus phi, a wave whose amplitude decays exponentially. Add an external periodic force and you get forced oscillation and the phenomenon of resonance. If the frequency of the external force matches the natural frequency of the system, the amplitude grows without bound in an idealized model. Resonance is what destroys bridges when soldiers march across them in step. All of this from a single differential equation with different add-ons. Newton's second law, F equals ma, is itself a differential equation. F equals m times d squared x over dt squared. Force equals mass times the second derivative of position with respect to time. Knowing the force, gravity for example, you solve this equation and get the trajectory, position as a function of time. This is how Newton derived the elliptical orbits of planets from the inverse square law. There are also differential equations that describe not individual bodies, but continuous media, fluids, gases, electromagnetic fields, heat flows. These are partial differential equations, PDEs. They contain derivatives with respect to several variables, spatial coordinates, and time. The wave equation, which describes the propagation of sound, light, and the vibrations of a string. Fourier's heat equation. The Laplace equation, which describes steady-state temperature fields and electrostatic potentials. Maxwell's equations, describing electromagnetism, are four partial differential equations from which follows the existence of electromagnetic waves, predicted by Maxwell in 1865 and experimentally confirmed by Hertz in 1888. Radio, television, Wi-Fi, cell phones, all are consequences of four equations written in the language of calculus. The Schrödinger equation, describing quantum mechanics, another PDE. The Navier-Stokes equations for fluid flow, also. Fourier's heat equation, also. The Boltzmann equation in statistical mechanics. The Lotka-Volterra equations describing predator-prey dynamics in ecology. The SIR model for the spread of epidemics. The Black-Scholes equation in finance. Virtually all of fundamental science is written in the language of differential equations. Calculus is the grammar of that language, and differential equations are its literature. One of the most astonishing aspects of differential equations is their universality.
One and the same equation can describe the decay of a radioactive substance and the cooling of a cup of coffee. One and the same equation describes the swing of a pendulum and the alternating current in an electrical circuit. Mathematics does not know about the physical content. It works with form, with structure. And it turns out that the most diverse physical processes share the same mathematical structure. Calculus lets you see that. But remember the crack in the foundation that Berkeley warned about? It had not gone away. All of these brilliant techniques, the power rule, substitution, integration by parts, differential equations, worked flawlessly. But they rested on the concept of infinitesimals, which no one could rigorously define. It was time to deal with the foundation. The crisis that Berkeley exposed in 1734 was not resolved within a year, or 10, or 50. For more than a century, mathematicians kept using calculus, kept getting brilliant results, and kept closing their eyes to the fundamental problem. Infinitesimals worked. Why they worked, nobody could explain rigorously. In many ways, 18th century mathematicians behaved like engineers building a skyscraper on sand. Every new floor was a brilliant feat of construction, but nobody checked whether the ground could hold it. And the ground held. Bridges stood. Planets flew along computed orbits. Cannonballs landed where formulas predicted. Practice worked. Theory limped. And the results kept multiplying. Joseph Fourier, who had worked in Napoleonic Egypt, he accompanied Napoleon on the expedition of 1798, and then returned to France, showed in the early 19th century that any periodic function, any wave, can be decomposed into a sum of sines and cosines.
The story of this discovery deserves a mention. Fourier was studying the propagation of heat, how a metal rod heats up when one end is placed in a fire. He wrote down the differential equation of heat conduction and looked for its solutions. And he discovered that the solution can be written as an infinite sum of trigonometric functions. Moreover, he claimed the method was universal. Any periodic function can be decomposed this way. A step function, a sawtooth, a triangle wave, anything, even functions with discontinuities. It is like a prism splitting white light into a spectrum. Each color is a specific frequency, and their sum gives white. A Fourier series does the same thing for any periodic signal. It decomposes it into a spectrum of frequencies. Low frequencies set the overall shape, high frequencies add fine details. Any wave, no matter how complex, a violin note, an ocean wave, an electrical signal, turns out to be a sum of the simplest harmonic oscillations.
Fourier's method became one of the most powerful tools in applied mathematics, used everywhere from audio processing to medical imaging, MRI, from image compression, JPEG, to seismic data analysis. But Fourier's proof was also not entirely rigorous. He claimed the decomposition works for any function without specifying what any means. For which functions does the Fourier series converge to the function itself? For which does it converge to something else? For which does it diverge? These questions demanded far subtler analysis than the early 19th century had at its disposal. And finally, people came along who tackled the foundation. The 19th century was the century of rigor in mathematics, when mathematicians stopped settling for intuitive arguments and began demanding proofs in the modern sense of the word. The first was Augustin Louis Cauchy. Cauchy was born in 1789 in Paris, the year the French Revolution began. His father, Louis-François Cauchy, was a civil servant who survived the terror by hiding in the countryside and later held a high post in Napoleon's government. The young Cauchy studied under Lagrange and Laplace, two of the greatest mathematicians of the previous generation, and became one of the most prolific mathematicians of his century. He published roughly 800 papers, a number surpassed only by Euler, and his principal contribution to calculus was the beginning of rigorous formalization. Cauchy introduced the concept of the limit as the central concept of analysis, replacing the vague infinitesimals. He replaced the phrase h is infinitely small with h can be made as small as you wish. The difference seems cosmetic, but it is fundamental. Infinitely small is about an object that needs to exist, and it is unclear how it exists if it is neither zero nor a positive number. As small as you wish is about a process. For any threshold given in advance, I can find an h small enough that, and then a specific inequality. Cauchy gave rigorous definitions of continuity. A function is continuous at a point if a small change in the argument leads to a small change in the value. And small is formalized through inequalities. He defined convergence of series through the concept of partial sums. He gave a definition of the definite integral close to the one we use today. Cauchy wrote two textbooks, Cours d'analyse, 1821, and Résumé des leçons sur le calcul infinitésimal, 1823, that laid the groundwork for a new, rigorous approach to calculus. Students admittedly complained. Before it was understandable, if not rigorous. Now it was rigorous, but incomprehensible. This complaint has accompanied calculus ever since. But Cauchy had gaps. His definition of the limit, though far more rigorous than his predecessors, still relied on an intuitive notion of infinite approach. The last, most fundamental brick was laid by Karl Weierstrass. Weierstrass, working in Berlin in the second half of the 19th century,
had an unusual biography for a great mathematician. He began his career as a schoolteacher in a small town in Prussia, teaching both mathematics and gymnastics. Yes, both. His mathematical papers were published in obscure school journals until one of them, on so-called abelian functions, caught the eye of professional mathematicians. It was so brilliant that the University of Berlin immediately offered him a position. Weierstrass was already past 40 at that point. It was Weierstrass who brought the formalization of analysis to its logical conclusion. He formulated the famous epsilon-delta definition of the limit, the definition you will encounter in any rigorous calculus course. Here is how it goes. We say the limit of f of x as x approaches a equals L if for every epsilon greater than 0, no matter how small, there exists a delta greater than 0 such that for all x satisfying 0 less than the absolute value of x minus a less than delta, the absolute value of f of x minus L is less than epsilon. In plain language, you tell me, I want the value of the function to be within epsilon of L. Epsilon is the tolerance, the accuracy you demand. I reply, fine, then take x within delta of a. Here is a specific delta. And f of x will be within epsilon of L. And I can do this for any epsilon, no matter how small. No infinitesimals, no ghosts. Only specific finite numbers and inequalities. A process, not an object. For every and there exists, quantifiers, the building blocks of mathematical logic. Let us illustrate with an example. We want to show that the limit of f of x equals 2x as x approaches 3 is 6. Intuitively obvious. Plug in 3, get 6. But the rigorous proof looks like this. We need to show, for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus 3, which is less than delta, then the absolute value of f of x minus 6 is less than epsilon. Substitute f of x equals 2x. The absolute value of 2x minus 6 is less than epsilon, which means 2 times the absolute value of x minus 3 is less than epsilon, which means the absolute value of x minus 3 is less than epsilon over 2. So we can take delta equals epsilon over 2, and the requirement is met, for any epsilon. Proof complete. Notice, nowhere in this proof are there infinitesimals, no h approaching 0, no ghosts. There are 2 specific positive numbers, epsilon and delta, and an inequality linking them. Everything finite, everything definite, everything verifiable. The epsilon-delta definition is not the most intuitive thing in the world.
Students encountering it for the first time often feel that things have gotten harder, not easier. And they are right, in the sense that rigor is always harder than intuition. But it is precisely this rigor that allowed calculus to be built on a solid foundation, where every statement is provable, every result reliable, and nobody can point a finger and say, as Berkeley did, there is a logical hole here. Weierstrass dealt another blow to mathematical intuition, and this one shook the entire community. He exhibited an example of a function that is continuous everywhere, but differentiable nowhere. Continuous means you can draw its graph without lifting your pencil from the paper. Nowhere differentiable means you cannot draw a tangent at any point. A curve that is broken at every single point, yet has no gaps. An object that contradicts all geometric experience. We are used to thinking that if a curve is smooth, continuous, you can lay a ruler against it at any point.
The Weierstrass function is built as an infinite sum of cosines with ever higher frequencies and ever smaller amplitudes. Each successive term adds jaggedness at an ever finer scale. The sum is continuous because the amplitudes decay and the series converges.
But at no point can a tangent be defined, because at every scale there are oscillations, and zooming in, making h smaller in the definition of the derivative, does not smooth them out. They keep interfering. Weierstrass showed that continuity and differentiability are different properties, and one does not follow from the other. For 19th century mathematicians, this was a shock. For us, who know about fractals, it is less surprising. Fractal curves, a coastline for example, are continuous but jagged at every scale. But in the 1870s, this was an earthquake. Around the same time, Bernhard Riemann gave a rigorous definition of the integral that today bears his name, the Riemann integral. Riemann is another tragic figure in our story. A genius mathematician who died of tuberculosis at 39, leaving behind relatively few works, but each one a masterpiece. The Riemann integral formalizes the very idea of partitioning into rectangles, summing, and taking the limit that we described earlier. Riemann did it rigorously, precisely specifying when the limit exists and when it does not. His approach: partition the interval from A to B into subintervals in any way you like. In each subinterval, pick any point. Compute the sum of the products of the function values at the chosen points and the lengths of the corresponding subintervals. If, as the partition is refined, as the maximum length of any subinterval approaches 0, this sum approaches one and the same limit, regardless of how you partitioned and which points you chose. The function is Riemann integrable, and that limit is the integral.
The beauty of Riemann's definition lies in its universality. It does not depend on the particular method of partitioning. You can partition into equal parts, unequal parts, however you like. If the limit exists, it will be the same. This makes the definition robust. The integral is an objective characteristic of the function, not an artifact of a particular method of computation. And then there is Georg Cantor, who in the 1870s and 80s plunged into the question that lay at the very foundation of calculus, but that everyone had been trying to avoid. What is infinity? Cantor asked a question that sounds absurd. Can you compare infinities? Is one infinity larger than another? It sounds meaningless. Infinity is infinity. But Cantor showed that there are not one, but infinitely many infinities, and that not all infinities are the same. The set of natural numbers, 1, 2, 3, is infinite. The set of real numbers, all points on the number line, is also infinite.
But there are more real numbers than natural numbers, in a strictly defined mathematical sense. What does more mean for infinite sets? Cantor defined it through the concept of one-to-one correspondence. Two sets have the same size if you can establish a one-to-one pairing between their elements. Every element of the first set matched to exactly one element of the second, and vice versa, with no gaps and no repeats. If such a pairing is possible, the sets are equinumerous. If not, one is larger. Natural numbers and even numbers are equinumerous. Pair each natural number n with the even number 2n, and you get a one-to-one correspondence. Even though there are seemingly half as many even numbers, both sets are infinite, and infinity does not obey ordinary arithmetic. This is already counterintuitive. A part can be the same size as the whole. But there really are more real numbers than natural numbers. Cantor proved this with his famous diagonal argument, an elegant proof by contradiction. Suppose we managed to list all the real numbers between 0 and 1, the first, the second, the third, and so on. Write their decimal expansions in an infinite table. Now construct a new number. Its first digit after the decimal point
differs from the first digit of the first number. Its second digit differs from the second digit of the second number. Its nth digit differs from the nth digit of the nth number. This diagonal number differs from every number in the list in at least one digit. So it is not in the list. But we assumed the list contains all real numbers. Contradiction. Therefore, listing all real numbers is impossible. There are more of them than natural numbers. Cantor's ideas provoked a storm. Many mathematicians rejected them, not because they found errors in the proofs, but because the results themselves seemed absurd. One of the leading mathematicians of the time, Leopold Kronecker, called Cantor a corrupter of youth and a charlatan, and actively obstructed his career, blocking publications, preventing appointments. Kronecker was a committed finitist. He believed that only finite constructions are legitimate in mathematics, and infinity is a fiction. God made the integers, he said. All else is the work of man. David Hilbert, another great mathematician, took the opposite view and defended Cantor. It was Hilbert who coined the famous line, "No one shall expel us from the paradise that Cantor has created." Cantor's work became a cornerstone of modern mathematics. The set theory he created is today the foundation on which all other branches are built. But in his lifetime, Cantor was broken by years of opposition, non-recognition, and intellectual isolation. He suffered bouts of severe depression, possibly bipolar disorder, and spent the last years of his life in a psychiatric clinic in Halle, Germany. He died on January 11, 1918, in the last year of the First World War, largely unrecognized by his contemporaries, though the next generation of mathematicians already understood the magnitude of his contribution. Cantor also formulated a conjecture that remains one of the most mysterious puzzles in mathematics to this day, the continuum hypothesis. The question is simple. Does there exist a set that is larger than the set of natural numbers, but smaller than the set of real numbers? An intermediate infinity between countable and continuum, does it exist? Cantor believed no such set exists, that between these two infinities there are no intermediates. He spent years trying to prove it and failed. In the 20th century, Kurt Gödel, in 1940, showed that the continuum hypothesis cannot be disproved within the standard axioms of set theory. It is consistent with them. Paul Cohen, in 1963, showed that it cannot be proved either. Its negation is also consistent with the axioms. Together, these results mean the question is undecidable. It can be neither proved nor disproved within standard mathematics. It escapes the system of axioms. This is one of the most astonishing results in the history of mathematics. There exist meaningful, concrete, precisely stated mathematical questions to which mathematics fundamentally cannot provide an answer. Not because we are not smart enough, but because the answer is not determined by the axioms we have adopted. The infinity that Archimedes tried to tame turned out to be even wilder than anyone could have guessed. But for our story, the key point is this. By the turn of the 20th century, calculus stood on solid ground. The limit was defined rigorously, through epsilon and delta, through quantifiers and inequalities, without ghosts or infinitesimals. The derivative was defined through the limit. The integral was defined through the limit. The fundamental theorem was proved. Taylor and Fourier series were justified. Conditions for convergence were investigated. Zeno's paradox was finally resolved. Achilles catches the tortoise because the sum of an infinitely decreasing series is finite.
Infinitely many steps can be completed in finite time if the duration of each successive step decreases fast enough. There is no paradox, only our intuitive error in handling infinity, which rigorous mathematics corrects. The building was rebuilt, from basement to roof.
What had begun as a collection of brilliant but logically dubious tricks became one of the most rigorous and reliable theories in all of mathematics. And the 20th and 21st centuries would show the scale of its power. If in the 17th and 18th centuries calculus explained the motion of planets and the flight of cannonballs, the 20th and 21st centuries revealed that its reach is far wider than any of its creators could have imagined. Let us start with what is closest to everyday life: MRI, magnetic resonance imaging. When a doctor orders an MRI, you lie inside a bulky cylindrical machine that generates a powerful magnetic field, tens of thousands of times stronger than the Earth's. The hydrogen atoms in your body, and there are inconceivably many of them because you are mostly water, align with the field like compass needles.
The machine then sends a radio frequency pulse that tips the protons, and as they return to their original alignment, they emit faint radio signals. Different tissues, muscle, fat, bone, tumors, return at different rates, and the machine distinguishes tissues by that difference. But the raw MRI data is not a picture. It is a set of frequencies and amplitudes, essentially Fourier coefficients. To turn that data into an image, those black and white cross-sections the doctor studies on a screen, the machine uses the inverse Fourier transform. The algorithm takes frequency domain data and reconstructs a spatial picture, exactly as a prism reassembles a spectrum into white light. The very method Joseph Fourier developed in the early 19th century to describe the spread of heat. Fourier did not know about magnetic resonance. He could not have imagined an MRI machine. He did not even know electromagnetic waves existed. Maxwell would predict them only half a century later. Fourier was studying how heat propagates through a metal rod, and he discovered that any signal can be decomposed into a sum of sine waves. This discovery turned out to be one of those rare mathematical results whose range of applications grows with every decade. 200 years later, the list of applications of the Fourier transform is longer than ever. Here is a partial list: speech processing, recognition and synthesis, crystallography, determining protein structures, for which several Nobel Prizes have been awarded, seismic data analysis, oil exploration and earthquake prediction, spectroscopy, analyzing the composition of stars by their light, electroencephalography, analyzing brain waves, radar signal processing, digital audio, telecommunications, and MRI, perhaps the most personally significant for each of us, GPS, the Global Positioning System. 24 satellites orbiting at an altitude of about 12,400 miles, each carrying atomic clocks.
The receiver in your phone picks up signals from several satellites and computes the distance to each by the difference in arrival time. The signal travels at the speed of light, and knowing the travel time gives you the distance. But here is a subtlety. The clocks on the satellite run slightly faster than clocks on Earth. Why? For two reasons. First, the satellite is farther from a massive body, the Earth, and according to Einstein's general theory of relativity, time in a weaker gravitational field runs faster. This is the effect of gravitational time dilation. Second, the satellite is moving at high speed, about 8,700 miles per hour, and according to special relativity, moving clocks run slower. The two effects act in opposite directions, but the gravitational one is stronger, and the net result is that the satellite clocks gain roughly 38 microseconds per day. 38 microseconds sounds trivial,
But light travels about 1,000 feet in 1 microsecond. Over a day, the error would accumulate to nearly 7 miles. Without corrections from the theory of relativity, GPS would become useless within a few hours. And the theory of relativity is written in the language of differential geometry, a branch of mathematics that rests entirely on calculus. Without calculus, without Einstein's differential equations, without the corrections of general relativity, GPS would be off by miles. With calculus, accuracy to within a few feet. Every time you open a map on your phone and see the blue dot on the right street, you are using the fruits of mathematics that started with Archimedes and passed through Newton, Leibniz, Euler, Riemann, and Einstein. JPEG image compression. When you take a photo on your phone and save it as a JPEG, the algorithm breaks the image into blocks of 8 by 8 pixels, and for each block computes the discrete cosine transform, DCT, a variant of the Fourier method using only cosines. The idea: each block of 64 pixels is represented as a sum of 64 basis patterns, from a uniform fill, lowest frequency, to a checkerboard, highest frequency. Each pattern has a coefficient, its weight, in that block. The human eye is good at distinguishing low-frequency components, overall shapes, smooth color transitions, and poor at high-frequency ones, fine details, sharp transitions. JPEG discards or coarsens the high-frequency coefficients and keeps the low-frequency ones. The result is a file tens of times smaller than the original, with visually negligible loss of quality. We sacrifice details the eye would not notice anyway, and save storage.
Every time you scroll through a social media feed and see photos, each one has been compressed and decompressed using the discrete cosine transform, a direct descendant of Fourier series. Streaming video, digital music, telecommunications, all depend on compression and signal processing methods that trace back to those same ideas of Fourier. When you listen to music through earbuds via a streaming service, the audio file was compressed by an algorithm that uses the Fourier transform to identify frequencies the human ear perceives poorly and remove them. The MP3 and AAC formats are mathematical descendants of Fourier. Computer graphics in video games and cinema is another field permeated by calculus. Surface lighting, reflections, shadows, refraction, all computed through integrals. Rendering a single frame of a Pixar movie can require millions of integral computations.
The physics of character movement, collisions, gravity, cloth and hair dynamics is described by differential equations that the computer solves in real time. Climate models that predict climate change decades into the future are systems of partial differential equations describing the circulation of the atmosphere and oceans, heat transfer, energy absorption and radiation, ice melt, and vegetation growth. These models partition the Earth's surface into millions of cells, and in each one solve the Navier-Stokes equations for air and water movement and the heat equation. Every forecast is the result of trillions of arithmetic operations, each implementing a discrete version of continuous calculus. Aerodynamics and aircraft design. An airplane wing has a specific profile. Its shape is not random, but engineered so that air flowing over it creates a pressure difference. The pressure above is lower than below, and that difference generates lift. The airflow around the wing is described by the Navier-Stokes equations, a system of nonlinear partial differential equations named after Claude Louis Navier and George Stokes. These equations are so complex that exact analytical solutions for real configurations are impossible, except for a handful of the simplest cases: laminar flow between parallel plates, pipe flow. For real problems, airflow around a plane,
a car, a building, engineers use computational fluid dynamics, CFD. They partition the space around the object into millions of small cells, finite elements or finite volumes, and solve the equations approximately in each cell, accounting for how the cells influence each other. This is, at its core, the same idea as Archimedes and Riemann's. Break the complex into many simple pieces and add them up.
The scale is just different. Millions of pieces, three-dimensional space, non-linear equations, and instead of paper and a stylus, a supercomputer performing trillions of operations per second. Incidentally, the question of whether smooth solutions of the Navier-Stokes equations always exist for arbitrary initial conditions in three-dimensional space is one of the 7 Millennium Prize problems, each carrying a $1 million reward from the Clay Mathematics Institute. As of today, this problem remains unsolved. We can approximately solve the Navier-Stokes equations on a computer, and that lets us design airplanes, but we still do not know whether mathematics guarantees that a solution always exists and behaves decently, does not blow up in finite time. The equations we use every day still hold fundamental secrets. In medicine, calculus works through more than just MRI.
Pharmacokinetics, the science of how drugs are distributed and eliminated from the body, is built entirely on differential equations. When a doctor determines dosage and frequency of a medication, behind that decision is a model in which rates of absorption, metabolism, and elimination are described by derivatives, and the total amount of drug in the blood at any moment is given by an integral. CT scanning uses a back projection algorithm based on the radon transform, a mathematical tool from the field of integral geometry. Financial markets. The Black-Scholes formula for pricing options, one of the most influential equations in the history of finance, was derived using stochastic calculus. Stochastic calculus is an extension of ordinary calculus to random processes, functions with built-in noise. Ordinary calculus works with deterministic functions. Plug in a value, get a definite answer.
Stochastic calculus works with functions containing random fluctuations, like a stock price that bounces unpredictably but obeys certain statistical regularities. The Black-Scholes formula, published in 1973, revolutionized the financial industry. It allowed, for the first time, systematic pricing of options, financial contracts granting the right, but not the obligation, to buy or sell an asset at a fixed price in the future. Myron Scholes and Robert Merton received the Nobel Prize in Economics in 1997 for this work. Fisher Black had already passed away by then. The key equation of stochastic calculus is Ito's lemma, discovered by the Japanese mathematician Kiyoshi Ito in the 1940s. Ito's lemma is, in essence, the chain rule for random processes. The chain rule that Leibniz wrote down in 1676, adapted to a world where functions jitter randomly.
The difference between ordinary calculus and stochastic calculus is subtler than it seems. In ordinary calculus, dt squared is approximately 0 and can be dropped. In stochastic calculus, dw squared equals dt, where w is a Wiener process, the mathematical model of a random walk, and it cannot be dropped. From this small difference grows an entire new theory. The Black-Scholes formula changed the financial world. It allowed proper pricing of options and hedging of risk. But the same formula, in the hands of people who trusted the model too much and forgot its assumptions, played a role in financial crises, including the collapse of the hedge fund LTCM in 1998, and, in part, the global financial crisis of 2008. Mathematics gives a tool, but responsibility for its use lies with people. Quantum mechanics. The Schrödinger equation, the fundamental equation of quantum mechanics, is a partial differential equation published in 1926. Its solution, the wave function psi, describes the probabilistic state of a quantum system. The square of the absolute value of the wave function at a given point gives the probability density of finding a particle at that point. To find the probability of finding an electron in a particular region, you integrate the absolute value of psi squared over that region. Without calculus, quantum mechanics is impossible, not in the sense that it would be hard to formulate, but in the sense that it literally has no language without calculus. Every calculation in quantum chemistry, from the shape of electron orbitals to the prediction of properties of new materials, involves solving the Schrödinger equation or its approximations. Semiconductors, lasers, transistors, all technologies based on quantum effects would be impossible without the mathematical apparatus that includes differential equations, eigenvalues, operators, and integrals. Richard Feynman, one of the greatest physicists of the 20th century, Nobel laureate, brilliant lecturer, legendary intellectual showman, went even further. He developed a formulation of quantum mechanics based on path integrals. The idea, at first glance, is insane. To compute the probability of a quantum particle going from point A to point B, you must sum up contributions from all possible paths between A and B, from a straight line to the most unimaginable zigzags across the entire universe and back. Each path contributes an amount determined by the exponential of the action, a functional that integrates the Lagrangian over time, and the integral over all paths gives the final probability. Feynman said a quantum particle tries all possible paths simultaneously. Paths far from the classical trajectory contribute amounts that cancel each other out, their phases scramble. Paths close to the classical trajectory add up constructively.
The result, the most probable trajectory coincides with the classical one. Quantum mechanics knows about classical physics. It contains it as a limiting case. This is a generalization of the Riemann integral to infinite dimensional space, and it remains one of the deepest and most technically challenging objects in mathematical physics. A rigorous mathematical definition of the Feynman path integral has yet to be completed. Mathematicians debate how to formalize it, but physicists use it every day, and it gives correct answers with fantastic precision. And finally, what would perhaps surprise Newton and Leibniz most if they could peer into the 21st century? Artificial intelligence. In 1986, David Rumelhart, Geoffrey Hinton, and Ronald Williams published a paper in the journal Nature describing an algorithm that allows training of multi-layer neural networks. This algorithm is called backpropagation.
The idea had existed earlier. It was independently discovered by several researchers, starting with Paul Werbos in 1974. But it was the Rumelhart, Hinton, and Williams paper that made it widely known and launched the wave of research that ultimately led to the modern revolution in artificial intelligence. And at the foundation of backpropagation lies the chain rule of differentiation, the very one Leibniz wrote down in 1675. Here is how it works in the broadest strokes. A neural network is a sequence of layers. Each layer takes input data, applies a set of transformations, multiplication by weights, addition of biases, passing through a non-linear function, and hands the result to the next layer. Data flows through the entire chain of layers, and at the output you get a result, the network's answer. For example, a recognized image, a translated sentence, or generated text. But at first the network cannot do anything.
Its weights, millions or billions of numerical parameters, are initialized randomly, and the answers are nonsense. Like turning 1,000 knobs on a control panel to random positions, the result will not be meaningful. Training consists of adjusting each of those knobs, each weight, so that the answers become meaningful. How? Through feedback. You show the network input data, a picture of a cat. It produces an answer, random nonsense. You compare the answer with the correct one. It should say cat. You measure the difference, the error, and you ask, which weights need to shift and in which direction to make the error smaller? For this, you need a measure of error, a loss function, that says how far the network's answer is from the correct one. The goal of training is to minimize this loss function, to find the set of weights at which the error is smallest. And here is where calculus enters. To minimize a function, you need to move downhill, in the direction where the function decreases. The direction of steepest descent is the negative gradient, a vector whose every component is the derivative of the loss function with respect to the corresponding weight, taken with a minus sign. Computing this gradient means figuring out how the error at the output depends on each individual weight in each layer. And here is where the chain rule comes in. A neural network is a composition of functions. The output of the first layer feeds into the second, the output of the second into the third, and so on. To find out how a weight in the first layer affects the error at the output, you need to trace the influence through the entire chain. The derivative through the whole network is the product of the derivatives at each layer. That is exactly what the chain rule says. The derivative of a composition equals the product of the derivatives. The backpropagation algorithm is a systematic way to compute this product of derivatives, moving from output to input, hence backpropagation. At each step, a local derivative is computed, the derivative of a layer's output with respect to its input, and passed backward, multiplied by the derivatives of the subsequent steps. Gradient descent, the minimization method, is based on a simple and beautiful idea. Picture a mountainous landscape. You are standing somewhere on a slope, and you want to find the bottom of the valley, the lowest point. Fog surrounds you. You cannot see far. What do? The most natural strategy. Look at which way the slope goes downhill right under your feet and take a step in that direction. Then look again, find the direction of steepest descent, take another step, and so on, step by step, always in the downhill direction. That is gradient descent. The gradient is a vector pointing in the direction of steepest ascent.
The negative gradient points downhill. Compute the gradient. Take a small step in the negative gradient direction, downhill. Compute the gradient again, because you are now at a different point and the slope may be different. Take another step, and repeat, thousands, millions, billions of times. With each step, the error, usually, decreases. The network learns. The step size, the so-called learning rate, is critically important. Too large a step and you overshoot the valley floor, bouncing back and forth without converging. Too small and training takes forever. Choosing the right step size is one of the key problems in practical machine learning. Here is what is happening. The network made a mistake. It gave the wrong answer. The algorithm computes. How sensitive is this error to each of the billions of parameters? To do this, it rolls the chain rule from output to input, layer by layer, factor by factor. It gets a vector of billions of derivatives, the gradient. Then it takes a small step opposite to the gradient, downhill. Recomputes the answer, measures the error again, computes the gradient again, takes another step, and so on, billions of times. After billions of such steps, the network, which started with random weights, has learned to recognize faces, translate texts, generate images, hold a conversation in human language. Each step is an application of the chain rule. Each step is a tiny movement toward a better set of weights. Infinitely many small steps, like Archimedes, like the definition of the limit, like the method of exhaustion.
The same fundamental idea. Get a good answer through an enormous number of small improvements. Every time you use a language model, facial recognition, a voice assistant, an image generator, behind the scenes, this process is at work. Billions of parameters, tuned through billions of gradient descent steps, each one an application of the chain rule.
The Leibniz rule from 1676. Inside every neural network on the planet. Moreover, the early history of deep learning hit a problem that is a direct consequence of the chain rule. If the multiplier, local derivative, at each layer is slightly less than 1, then multiplying hundreds of such factors by the chain rule yields a vanishingly small number. Imagine multiplying 0.9 by itself 10 times. 0.9 to the 10th is about 0.35, already a noticeable shrinkage. 100 times, 0.9 to the 100th is about 0.000027, practically zero. If each layer in the network slightly squeezes the gradient, then after 100 layers the gradient becomes negligibly small, and the early layers essentially stop learning. All the error information is lost along the way.
The reverse problem also exists. If the multipliers are greater than 1, the gradient grows exponentially, the exploding gradient. The model goes haywire, weights scatter, training becomes unstable. The solution came through architectural innovations, activation functions that do not squeeze the gradient. ReLU, rectified linear unit instead of the sigmoid. Skip connections, residual connections, proposed in 2015. Layer normalization, careful weight initialization. Each of these solutions is essentially an engineering response to a mathematical problem that flows from the properties of the chain rule applied to a long chain of multiplications. 17th century mathematics breeds 21st century engineering problems. There are other areas where calculus is actively expanding right now.
Neural ODEs. Neural ordinary differential equations are an approach in which a neural network is viewed not as a discrete sequence of layers, but as a continuous dynamical system described by a differential equation. Instead of saying layer 1, layer 2, layer 3, you say the system's state evolves continuously in time according to a differential equation whose parameters are learned. This unites two great ideas, neural networks and differential equations, and opens new possibilities for modeling continuous processes. Graph neural networks apply learning to data living on graphs, social networks, molecular structures, knowledge bases. Researchers are developing graph calculus, extending the notions of derivative and differential equation to discrete structures. What does a gradient mean on a graph? How do you describe diffusion of information across a network? These questions are under active investigation, and the answers draw on ideas from continuous calculus adapted to discrete structures. Differential geometry, the branch of mathematics that generalizes calculus to curved surfaces and higher dimensional spaces, became the language of Einstein's general theory of relativity and the basis for modern research in string theory and quantum gravity. The concept of curvature of spacetime, central to Einstein's theory, is defined through second derivatives of the metric tensor. Without differential geometry, that is, without calculus generalized to curved spaces, modern cosmology would be impossible. The Riemann hypothesis, one of the most famous unsolved problems in mathematics, another of the 7 Millennium Prize problems, makes a claim about the zeros of the Riemann zeta function, an object of complex analysis.
The zeta function. Zeta of s equals 1 over 1 to the s, plus 1 over 2 to the s, plus 1 over 3 to the s, and so on, is an infinite series that converges when s is greater than 1 and can be analytically continued to the entire complex plane. Riemann discovered that the zeros of this function, the values of s at which zeta of s equals 0, are intimately connected to the distribution of prime numbers. His hypothesis asserts that all the non-trivial zeros lie on the line where the real part of S equals 1/2 in the complex plane. If true, it would have profound consequences for our understanding of how prime numbers, the building blocks of arithmetic, are distributed among the natural numbers. Mathematicians have been working on the Riemann hypothesis for more than 160 years. P-adic analysis and non-Archimedean analysis are areas where calculus is built not on the familiar real numbers, but on other number systems with different notions of closeness and limit. In ordinary numbers, 1,000,000 and 1,000,001 are close, while 1,000,007 are far. In p-adic numbers, the notion of closeness is defined through divisibility by a prime number p. Two numbers are close if their difference is divisible by a high power of p. This is a completely different geometry, a different topology, and yet you can build calculus in it, defining derivatives and integrals. P-adic analysis finds applications in number theory. Andrew Wild's proof of Fermat's last theorem uses p-adic methods. In cryptography and in theoretical physics, p-adic quantum mechanics and p-adic string theory. Calculus is a living, expanding field of mathematics that continues to surprise more than 4 centuries after its creation. Calculus, born from the question, what is the area of this curved shape, turned out to be capable of describing the motion of planets, the propagation of heat, the behavior of electromagnetic fields, the probabilistic state of quantum particles, the evolution of financial markets, and the training of artificial intelligence. One and the same mathematical structure, limits, derivatives, integrals, in all of these utterly different domains. This tells you something about the deep structure of the world. Change is everywhere. Calculus is the language humanity developed to talk about change. The Nobel laureate in physics, Eugene Wigner, wrote a famous paper in 1960 titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." He asked, why does mathematics, created by humans, abstract, detached from reality, born of logic and imagination, describe the physical world so unreasonably well?
Why do equations devised to solve one problem turn out to be applicable to an entirely different one? Why are complex numbers, invented as an algebraic trick, necessary for describing quantum mechanics? Why did non-Euclidean geometry, created as a logical exercise, become the language of general relativity? Calculus is perhaps the most vivid example of this unreasonable effectiveness. Newton wanted to describe planetary motion, Fourier, the spread of heat, Schrödinger, the behavior of electrons, Black and Scholes, the price of an option, Hinton, the training of a neural network. All of them used one and the same mathematical apparatus, and it worked every time. As if the universe were written in the language of differential equations, and calculus were the key to deciphering it. As if behind the visible diversity of phenomena, gravity and electromagnetism, heat and sound, the motion of planets and the motion of stock prices, there stood one and the same mathematical structure. Continuous change, limit, derivative, integral. 3 words, 4,000 years, an infinite number of applications. We have come a long way. Let us look back and see what distance we have covered. 4,000 years ago in Egypt, someone wrote down a formula for the volume of a truncated pyramid, whose rigorous derivation requires an integral. In the same era, the Babylonians were adding up the areas of trapezoids under a graph of Jupiter's velocity, doing what we would now call integration. Neither the Egyptians nor the Babylonians generalized their methods. They solved specific problems with brilliant tricks, but they touched something deep, an idea that would keep surfacing again and again.
Archimedes, 2,300 years ago, on Sicily, inscribed infinitely many triangles inside a parabola and crept toward the exact area. He could not say limit. He did not have the word. But his method of exhaustion, the first systematic use of infinite approximation to obtain exact answers, was the seed from which all of calculus would grow. And in a secret treatise, discovered 2 millennia later, he worked with infinitely thin strips, exactly as Leibniz would. Liu Hui in China, in the 3rd century of the Common Era, independently invented the method of exhaustion for computing the area of a circle. The same idea, a different continent, a different century. Ibn al-Haytham in the Islamic world, around the turn of the 1st and 2nd millennia, worked with sums of powers, problems directly connected to computing integrals of polynomials.
Madhava and the Kerala school, in the 14th and 15th centuries in India, developed infinite series for trigonometric functions, computed pi to 11 decimal places, and worked with concepts equivalent to derivatives. 250 years before Europe. Descartes united algebra and geometry, creating the coordinate plane, a bridge without which calculus in its modern form would have been impossible. Fermat developed methods for finding maxima and tangent lines. Cavalieri proposed the method of indivisibles. Barrow saw that finding areas and finding slopes are inverse operations. Newton, at 22, hiding from the plague, created the method of fluxions, differential and integral calculus in a physical formulation. Connected calculus to mechanics. Explained why planets move in ellipses, and did not publish out of fear of criticism.
Leibniz, independently, coming from geometry and differentials, dreaming of a characteristica universalis, a universal language for all thoughts, created the same calculus in a different formulation, with brilliant notation the whole world still uses today. Wrote the integral symbol on October 29, 1675, and published, and was destroyed. Their war over priority split European mathematics for decades. Leibniz died unrecognized. British mathematics, out of loyalty to Newton, refused the more convenient notation and fell behind the continent by a century. The Bernoulli brothers, Euler and others, revved the calculus machine to incredible speeds, solving problems in physics, geometry, astronomy, and probability. Euler introduced most of the notation we use. Fourier showed that any wave can be decomposed into a sum of sines and cosines. But all this time, the foundation remained shaky.
Infinitesimals, the ghosts of departed quantities, worked but were not logically justified. Cauchy and Weierstrass poured a new foundation, a rigorous definition of the limit through epsilon and delta. Riemann formalized the integral. Cantor showed that there are infinitely many orders of infinity and paid for it with his sanity. By the end of the 19th century, calculus became what it had not been before. Not only powerful and practical, but logically impeccable. And the 20th and 21st centuries revealed the scale of that power. MRI, GPS, data compression, aerodynamics, financial models, quantum mechanics, general relativity, machine learning, robotics, climate modeling, bridge and skyscraper calculations, cryptography, speech processing, computer graphics, nuclear reaction modeling. The list could go on forever. The Leibniz chain rule inside every neural network. The Riemann sum in every numerical simulation. The Fourier series in every compressed image and every streaming video. Newton's differential equation in every orbital calculation. One and the same mathematical language, limits, derivatives, integrals, describes the path of a planet, the spread of a disease, the compression of a photograph, the training of a neural network, and the age of a bone from an ancient Egyptian burial. This tells you something about the deep structure of the world. Change is everywhere. Calculus is the language humanity developed to talk about change. Galileo said in the 17th century that the book of nature is written in the language of mathematics,
If so, then calculus is its grammar.
And now you are lying here, and the night is quiet, and everything we talked about, the Egyptian papyrus, the Babylonian tablets, Archimedes with his triangles, Madhava with his series, Newton in plague quarantine, Leibniz in his Hanover study, Euler, Cauchy, Weierstrass, Riemann, Cantor, Fourier, Feynman. All of them were pulling the same thread. A thread that began with the question, what is the area of this curved shape? And led to the language in which the physics of the universe is written. Think about how little it takes to start. An Egyptian needed to know how much stone to order for a construction project. A Babylonian, where Jupiter would be next month. Archimedes, what the area of a parabolic segment was. Madhava, what pi equaled. Newton, why planets move in ellipses. Leibniz, how to find the tangent to a curve. Fourier, how heat spreads in a rod. Each of them started with a concrete, practical, tangible problem. And each, solving their problem, discovered something universal. A method that works not only for this specific shape, this specific trajectory, this specific rod, but for any shape, any trajectory, any process where something is continuously changing. Each generation contributed its part. Each civilization added its fragment. One generation's tool became the next generation's foundation, which in turn became so familiar that the generation after that did not even notice it, the way we do not notice the air we breathe. Descartes' coordinate plane. We draw graphs without pausing to consider that before the 1630s, no such possibility existed. Leibniz's notation. We write dy over dx without realizing that behind those four symbols lies a titanic effort to create a symbolic language for describing change. The epsilon delta definition of the limit. We learn it in the first year of college without recognizing that for 1500 years, the greatest minds could not formalize what seemed intuitively obvious. There are people who are afraid of calculus, who remember it as a subject where they were buried in formulas without being told what any of it was for, where they learned differentiation rules without understanding that the derivative is the instantaneous rate of change, where they computed integrals without grasping that they were summing infinitely thin slices into a whole, where the entire subject felt like a pile of pointless tricks invented to torment students. And here is what I want to say, lying here at the end of this long journey. Calculus is not about formulas. The formulas are a notebook. Calculus is about a way of seeing the world, about the ability to look at something that is continuously changing and understand how it is changing and how much change has accumulated. Calculus is one of the best things humanity has ever produced. And the word produced is perhaps not quite right. More like discovered. Because the ideas were always nearby, always waiting, in the shape of a parabola, in the motion of planets, in the curvature of a coastline, in the speed at which tea cools, in the rhythm of a beating heart, in the rainbow that splits white light into a spectrum. The question, was mathematics invented or discovered, is one of the oldest in the philosophy of mathematics, and we will not try to answer it here. But the history of calculus, with its many independent discoveries of the same ideas on different continents, strongly suggests that at least some mathematical structures exist in some sense independently of us.
Too many people, in two different circumstances, by two different paths, arrived at the same results for it to be coincidence. All it took was someone to look closely enough. And now, you can close your eyes. Think about the fact that right now, in this second, around you and inside you, calculus is at work. The air temperature in the room is changing ever so slightly. Molecules of air collide, exchanging kinetic energy, and the rate of that change is described by a derivative. The blanket is transferring heat to your body according to Fourier's law. The rate of heat transfer is proportional to the temperature difference, and that proportionality is written as a differential equation. Your heart is beating, rhythmically but not perfectly evenly. The electrical activity of the heart, recorded on an ECG, is a wave that can be decomposed into a Fourier series. Cardiologists use this decomposition for diagnosis. Certain frequency components signal arrhythmias or other problems.
The electrical signals in your brain, alpha waves, beta waves, the delta waves of deep sleep, also decompose into Fourier series, and an EEG essentially shows the spectrum of brain activity. Blood flows through your vessels, and the flow of blood is described by the Navier-Stokes equations, the very same equations that describe airflow around an airplane wing. If you took a medication, it is distributing through your tissues and being cleared by your kidneys. And that process is described by a pharmacokinetic differential equation. You are a quantum system made of atoms, the behavior of each of which is described by the Schrödinger equation. You are a biological system, the growth and division of whose cells are described by exponential differential equations. That same formula, dy over dt equals ky, that we discussed, your body is solving it right now. Renewing intestinal cells every 3 to 5 days, skin cells every 2 to 3 weeks. You are an electrochemical machine, each nerve impulse of which is a solution to the Hodgkin-Huxley equations, a system of 4 nonlinear differential equations describing the flows of sodium and potassium ions through a neuron's membrane. Alan Hodgkin and Andrew Huxley received the Nobel Prize in Medicine in 1963 for this work that would have been impossible without calculus. Even the process of falling asleep, the gradual slowing of neural activity, the smooth transition from wakefulness to deep sleep, is described by mathematics in which continuous change, derivatives, and integrals play a central role. There is something calming in the thought that the world, for all its complexity, is described by such simple ideas. Limit, derivative, integral, 3 concepts. From them, all of physics, all of engineering, all of modern technology. 3 concepts that humanity spent 4,000 years approaching, and that once finally formulated, turned out to be so deep that they sufficed for everything else. Calculus is a description of how the world works, the world in which you live and in which you are now falling asleep. Maybe the most amazing thing about this 4,000-year story is that it is not over. Calculus continues to expand, to penetrate new fields, to find new applications. Each decade brings surprises. Who could have predicted that the chain rule of the 17th century would become the engine of 21st century artificial intelligence? That differential equations, devised for describing planetary orbits, would be used to model the spread of epidemics and predict the weather? That Fourier series, invented for describing how metal cools, would become the foundation of digital music and medical imaging? The next chapter of this story has not yet been written. Perhaps among those listening to this tale, there is someone who will write it. 4,000 years, dozens of civilizations, hundreds of minds. One idea. If the world is continuously changing, you can understand that change by breaking it into infinitely many, infinitely small pieces and putting them back together. Approaching infinitely without touching. getting an exact answer from infinitely many inexact steps, catching the instant without stopping time, counting the whole by summing the infinitely small. That is the whole magic. And it works. It worked 4,000 years ago when a Babylonian was drawing trapezoids under a graph of Jupiter's speed. It worked 2,300 years ago when Archimedes was inscribing triangles inside a parabola. It worked 350 years ago when Newton was writing his method of fluxions into a notebook by candlelight. It works now, as a neural network adjusts billions of weights, learning to generate text.
It will work 1,000 years from now, in applications we cannot imagine today. Just as Leibniz could not imagine a neural network, and Archimedes could not imagine GPS. You have passed through all the layers, from the surface to the very bottom and back, from the clay of Mesopotamia to the silicon of data centers, from Archimedes to algorithms. You can let the thoughts go now. They will settle overnight, like the terms of a convergent series, each a little smaller than the last, but together giving an exact answer. A Babylonian drawing trapezoids under a graph of Jupiter's speed 4,000 years ago had no idea someone would one day lie in the dark thinking about him. Archimedes, inscribing triangles inside a parabola, did not suspect his method would live inside machines capable of composing music. Madhava, writing infinite series in Kerala, could not have imagined that those same series would be computed trillions of times per second inside processors the size of a fingernail. Newton, sitting in plague quarantine and discovering the laws of motion, did not expect his equations would guide spacecraft to other planets. Leibniz, dreaming of a universal language of thought, did not guess his notation would outlive him by 3.5 centuries and become the standard for all of world mathematics. Each of them was pulling the same thread. And tonight you touched that thread. A thread that stretches across 4,000 years, across dozens of civilizations, through wars and plagues, through brilliance and tragedy, from clay tablets to silicon chips, approaching infinitely without touching, catching the instant without stopping time, counting the whole by summing the infinitely small. Close your eyes, breathe steadily. Good night.